Good afternoon, ladies and gentlemen, and welcome to the Direct Air Capture Summit 2020. Today, I'm super happy to be here with you all, and also a warm welcome to our online audience. We are here in the Kunsthalle, but we have many online visitors around the globe. I'm happy to be here with you, and this has several reasons. You can imagine what. First is my own story, related to creating a better future for humanity. Second, it is the current situation under which I think now and today is a very special moment in time to meet together here and experience live events together. And third, it's my and our passion for new technologies like direct air capture, carbon dioxide removal, and carbon capture storage. These technologies are a key instrument we are now holding in our hands for creating a better future for humanity and a better future for generations to come. As I said, I have my personal story towards creating a better future for humanity. My name is Niels Müller, and I'm the CEO and founder of Trend One, a global trend research and foresight company based in Germany and Switzerland. Our vision is to create the best 21st century. So for me, today, there would be no better place in the whole galaxy than being together with you on this amazing conference. We not only have amazing speakers, we have also many professors from ETH Zurich, leading players from the industry like carbon engineering, Global Thermostat, so this is a true platform for discussing climate solutions. All together, we here in the room, you as experts and the speakers, and we all together. So now is my very special to invite the founders and directors of Climeworks together with me on stage, Jan and Christoph. Welcome and thank you for organizing this.
Thank you, Niels. Somehow, things related to the three letters D, A, C are especially challenging. Similar as to developing technologies for capturing CO2 from the air, organizing the summit has been quite adventurous. The more thankful we are that all of you are here. We are very, very thankful for the speakers to reconfirm their attendance even after shifting the dates, and we are very thankful to have you, our guests, with us. For us, this is indeed a very strong signal that climate change remains high on the agenda, despite the quite challenging and severe situation we're in at the moment. And, well, it's actually an interest, or I've never talked to an audience like this. You should see yourself. Maybe you can look in the online version, in the recording later. Our motivation to organize this, or the idea and motivation to organize this, was really to provide education, first-hand education or experiences from the field in the whole value chain of direct air capture. We perceive that more and more people in science, but also in politics, as well as in economy, are more and more discussing and also considering direct air capture. And there are even some policies and companies that already implemented direct air capture in their plans for rescuing the climate. And in such, today, we really want to provide this education to enable informed decisions. Well, with that, I would like to welcome you to the first Direct Air Capture Summit, and I hope we will provide fruitful insights throughout the next hours.
Thank you. Yeah. Thank you, Christoph.
Just one final remark. I just made a small inquiry before with several people. When was the last time you have been standing in front of a real audience? And everyone said, well, I don't know. It's like half a year ago, something like that. So we are very, very thankful that you all made it here. Thankful to our speakers. And I think talking about direct air capture and carbon removal is really a very good and fitting occasion to start again in some form with a different format, with a couple of masks around, to start meeting in such a group. So looking very much forward to it.
Thank you, Jan. So before we start with our amazing speakers, the Corona rules, but you already know, I have to tell you, wear your masks, 1.5 meter distance, no handshake, never use the same coffee cups, but you can cheers and say hello and you can prost to each other. So looking forward to the summit. We will have a break, a coffee break later. There are also some guests and experts from Climeworks walking around, supporting you in the Corona rules, so all questions you have. Our first speaker today is a luminary expert. In Germany, we say it's a real coryphée in climate solutions. He's a world-renowned scientist. Reto Knutti was the coding lead author of the 4th and 5th assessment of the IPCC. So please welcome with me, live on stage today. Thank you for coming, Professor Reto Knutti, and give a warm welcome to him. Reto will give the big picture on climate solutions. Thank you.
Thank you, Niels, for the introduction, and good afternoon. It's a pleasure to be here. Just as a disclaimer, I have no affiliation whatsoever with any of the companies that are doing work here. I'm just a climate scientist and trying to set the stage a bit of why are we talking about these things in the first place. And let me start with a few pictures. This is from 2018 in the Jura, for those who know the picture. The driest summer recorded in measurements since about 1860 or so. This is from Australia, but you could show similar pictures from California these days. This is just days ago, Laura, in the Gulf of Mexico. So you wonder what's going on. And you don't wonder just about the science and the nature out there, but you also wonder about what society is thinking. Of course, things have completely changed in the last 2 years. The public's debate with the climate strikes and so on. Here's another example from what is called Gletscher Initiative in Switzerland. All the experts said, are you crazy? Are you crazy trying to get a goal of 0 emissions into the Verfassung? And within a few months, they got the 100,000 signatures to do that. And a year ago or so, even the Swiss government, which is not necessarily always the fastest, said we're going to go for 0 greenhouse gas emissions by 2050. 0. If you just picture that for a moment, and then you realize that 0 doesn't mean like you're going to save a little bit of energy here and there and get a bit more efficient, but 0 basically means nothing, right? There's nothing left. There's no combustion engine left. There's no CO2 that you emit unless you're going to take it out of the air somewhere, which requires a fundamental rethinking of how we produce energy. But let's go back a little bit and see where are we coming from? Why this 0 emission goal? Of course, the first thing you have to recognize is climate change is happening. The quote here from the top, warming of the climate system is unequivocal. It's been for a while, but here's the picture from Switzerland, 1860 to today on the right, and you can see the last 30 years were completely unusual in Switzerland. 2 degrees warming over the last century, 1 degree worldwide. If you don't believe the thermometers, then go into the mountains. 1850 on the left, the Rhone Glacier, and towards the end of the 20th century. On the right, if you stand at this position, you wouldn't see any glacier today. So things are obvious. Something is happening. What's the cause? Most of the warming is extremely likely to be due to human influence, and the human influence is pretty obvious. And one way to show it is you go to Antarctica here, and you drill into the ice and you reconstruct CO2 and methane levels on the air bubbles recorded in ice. You have 800,000 years at least of climate history, and you can see that things have changed over the past. The climate has varied over the past from the ice ages and warmer phases, but then at the very end today, something is happening which is pretty amazing. I mean, I guess if you've seen this before, so I'm not going to spend too much time. Obviously, the change in the CO2 and methane concentrations are massive, and they're massively fast. So we know where this is coming from, and we know, of course, the basics of what's happening because of the laws of physics. So if I take this glass here, sorry, I've just touched your glass. You shouldn't touch it anymore. If I
Now it's yours.
if I drop this, it's going to fall down, not up. Right? You can test it at home, but take a cheap glass. It always falls down because it's the laws of physics. And the laws of physics, if you solve them in a computer, this is what you get. This is not observed data. This is a simulation of fluid dynamics on a rotating sphere. And you see the storms not because I told this thing to make a storm, but it's just because fluid dynamics works the way it works. Right? Conservation of energy, conservation of mass, and so on. So the laws of physics and the greenhouse effect are at least 100 years old. The basics go back to 1850. So we know why. The impacts are obvious. If you go to the future, you can do different scenarios. Here's two bracketing scenarios that are often used. On the left would be something that is approximately consistent with a 2-degree target as agreed in Paris. On the right would be something like a high emission scenario. You can debate whether that's realistic or not, but it assumes more fossil fuel emissions than in the past. That would be something like 4 degrees from present or so. And on the bottom, you could try to downscale that and say, for instance, how many days over 30 degrees peak temperature you would get. And you can see on the right, you would get to every other day in summer would be above 30 degrees. So the impacts are obvious. They're obvious for health, for agriculture. They're obvious for glaciers. This is the longest and largest glacier we have in Switzerland at this point, the Aletsch Glacier. And you can see by the end of the century, even that is gone in a high emission scenario. That's pretty impressive given that there's about 700 meters of thickness of ice at the Concordia Platz, if you've ever been there. We know a lot about the impacts, but of course there are still some uncertainty in local adaptation. And just to demonstrate that in a beautiful animation, this is what you get when you do weather forecasts on a 1 kilometer grid scale. The blue is rainfall, and I'm showing this to demonstrate how quickly these things change, how these rainfall patterns move, and how small scale they are. And then you appreciate that it's not possible at this point to estimate what the detailed impact of climate change will be on every small part of the world. So we know something, but we also have to live with a certain degree of uncertainty, and we have to come up with strategies that are sort of working well under a broad range of future outcomes. So, we know something about impacts and adaptation. We know a lot about CO2 reduction, and the basic message, I think, is that, of course, I'm biased because we were largely responsible for that. That was back in the 5th Assessment Report 2013 of IPCC, where we had one of the figures in the summary for policymakers showing an almost, I mean, it looks like pretty straightforward, simple relationship between total emitted CO2 and temperature. And the basic message is that the two are approximately linearly related. So you start from the left and you go up to the right and to the top as time moves on through various scenarios. It's pretty straightforward. It wasn't straightforward back then, I can tell you. It took us about 6 hours or so to get this adopted by the government. It was the most difficult part to get adopted in the negotiations, not because the science is hard, but because it was inconvenient. It's something that people don't usually know, and that's why I'm telling the story. The governments were fine with predictions and projections of future temperature and rainfall. That didn't matter. These were scenarios that you could just make them up, right? But as soon as we were plotting carbon and temperature on the same figure, they got really, really nervous, right? And I had one government delegate telling me that, well, she could see that if two things were linearly related, one could go from the horizontal and then estimate what the temperature would be on the vertical, but she couldn't see how one could go from a temperature target back to a CO2 emission target. So if X and Y are proportional, you could go from X to Y, but not from Y back to X. It was politically inconvenient. Oh, but of course it's pretty straightforward, namely that every ton emitted creates a certain warming, no matter when you emit it and where. Right? It doesn't matter. You can shift it around. It also implies, of course, that every temperature target that you set, whether it's 1.5 or 2 or 2.5 degrees, implies a certain amount of carbon that you can emit. And then you have to stop. And that means at some point the emissions need to get to zero. It also means that once you've emitted a certain amount of carbon, the temperatures are pretty much going to stay there for a very, very long time, hundreds if not thousands of years. And the only way to reverse it is to take the carbon back out of the atmosphere. Of course, now we can debate how much exactly we have. So if we had a perfect relationship, we could take 2 degrees or 1.5 degrees and estimate the carbon budgets. We have a somewhat more complicated situation that we have other gases that affect the radiation budget. So if you have a non-CO2 here on the right, on the red, in red, if that's positive, of course, that lowers the amount of carbon you can emit. An additional complication is that the best estimate, the black line, would only tell you with a 50-50 chance how much carbon you can emit, or you would have, in other words, a 50-50 chance of failing to reach your target. Then the more certain you want to be, the lower the amount of carbon you can emit. And then, of course, the lower your temperature target, the lower the carbon budget. So the exact number we can debate, but it's something along the 10 or 15 years of current emissions. We're talking about approximately a decade of current emissions for the targets that have been discussed. So what does that mean in time? The high emission scenario, RCP 8.5, which is maybe on the high side, but it's not completely impossible, would look something like this in terms of emissions per year. If we had started early, these are so-called the perfect foresight, perfect collaboration scenarios from integrated assessment models, then you would do something like this. So you would start early and then reduce gradually. Usually we're a bit more stupid and we do something like this. This would also bring you to the same temperature target. The more you emit in the early phase, the faster you have to reduce, and the more negative you have to go in the later phase, and you can see by eye that the total emitted carbon is about the same. Right? Except that the red one is going to be more expensive and harder. Right? The longer you wait, the harder it gets, the less flexibility you have in terms of developing these solutions. And that's why we're arguing that we shouldn't wait and delay these things. But what is obvious here is that you get to zero at some point. Here's about 2060 or so. That's for 2 degrees. If you talk about well below 2 degrees, then we get to something like 2050, right? Plus minus a few years. It doesn't matter. But you can see that I think the debate has shifted. Here's a map that I just found yesterday. All the countries and cities that are somehow having a net zero target somewhere, either in the political discussion or already in legislation. Clearly, the countries have recognized that this zero goal is important. Right? Where is the carbon? Here's the example from Switzerland. It's about a quarter or so in road transportation. A massive 19% in Switzerland, that's assuming a factor of 2 for the indirect effects. 19% is in aviation. It's a lot. Of course, globally it's less because most people don't fly, but the growth rate is very large. Then it's in buildings, it's in manufacturing, agriculture, services, and waste. These are all greenhouse gases. The bottom line is it's essentially everywhere, and different sectors will need different measures. Some of these are easier than others. Road transportation may be easier with electric cars and hydrogen and so on, but there are some that are really hard. Aviation is one, cement is one, and agriculture is one. And so when you have emissions that are hard to avoid, then you need a way to compensate somehow. And that leads us to all these technologies, which I'm not going to comment on in detail because there are people in this room who know much more about these negative emission technologies. Just a few, essentially 3 points or so. The first is that people talk a lot about afforestation and reforestation. And I know my institution is partly responsible up the hill here for putting out studies that I don't think are capturing everything that they should. The reality is that planting trees will not solve the climate change problem. Planting trees may be useful in certain contexts for conservation efforts, but where you could potentially plant a tree and where you will actually likely in practice plant a tree are two very different things. Second, the trees are growing slowly and it's a one-time thing, so this is not going to be enough. You need other technologies. The second comment is that you do need investments somewhere. These things do not come for free, so you probably need some kind of a price on carbon. You do need investments on both research and infrastructure to scale these things up. Right? And the third, and that's important, is that all of this should not take the focus away from the necessary decarbonization and mitigation. Right? We probably have to do 80% by avoiding emissions and the remaining 20% for the things, so that the remaining 20% should be by negative emission technology for things that we cannot avoid or things we have done wrongly in the past, so that would be the only way of getting the carbon out of the atmosphere that we have missed in the past. Summary, I've tried to show quickly that climate change is real, humans are mostly responsible, and most of the effects are negative. We don't really have much time, but what we do today will affect the world for many centuries, and much of it is in fact irreversible unless we manage to extract the carbon from the atmosphere. We need to go to zero by around 2050 plus minus something, and we're not on track. Clearly, both Switzerland and globally, we're not on track. And I've argued that planting trees is not sufficient. We need other technologies, and that needs research and infrastructure because it's not going to happen just by chance. Thank you very much.
Reto, you have an amazing ability to explain science language to a broader audience. We just experienced this. So we all see this is really science fact. But the question is, how can we explain all this to a broader audience, to governments, to companies, to society? Because there's so much in there, including all the tipping points we will maybe meet the next 10 years, like Iceland and all this tipping points we have. And this is so complex system thinking. How could you better explain this to a broader society and governments and business?
Well, I try to do it every day, but yes. I don't think it's actually that hard, right? I mean, the basic message that you need to go to zero emissions isn't that hard.
Yeah.
I think the idea that you just have to explain the facts and then the political action will happen is wrong. And people are a bit lazy, they're a bit stupid, and they're a bit selfish, and it's not because we don't understand the science, it's because we have other motivations and other priorities. So we need a shift in priorities, and that needs political boundary conditions, and it needs a price on carbon, yes, so that everybody realizes this is the way we're going.
All right, all right. So we now see some companies moving in the right direction, right? Like Microsoft, Apple, Swiss Re, they all work on this topic. How do you compare this business initiatives compared to governmental initiatives?
Well, I think it needs both. The government is needed to get those on board who are not willing to do it, right? But the businesses are important because they can change quickly. I think the financial sector is really interesting. They can change from one day to another by changing investments. And they have also a reach that goes far beyond Switzerland. Right? I mean, Switzerland has a lot of money also abroad. So if these big companies change, that could have trickle-down effects that are far beyond the size of our country.
Right, right. If you look at carbon dioxide and direct air capture technology today, I like to compare it to the first propeller engines and flights in 1900, and now we have like supersonic jets. Where are these carbon contractors today? Where is this technology today compared to the flight industry? Are we still in the beginning?
It's hard for me, of course, as a climate.
How much room is there for improvement?
I think that the basics are essentially there, but it needs to get cheaper, it needs to get more effective, and that needs infrastructure and investments. I think that scaling up is just as important as the research, and I think people are understanding that, and the governments are also understanding that. We cannot do without. Switzerland just a few days ago set out the report, and the government basically said, yes, we need to set the boundary conditions for this to move forward. And I hope that in 10 years we're going to have another event here and we'll be able to say, yes, things have made progress.
Yes, all right. Any questions from the audience?
They all know the science.
Marco Mazzotti, so you said that we need infrastructure. Can you be more specific? What type of infrastructure we need? Of course, you shouldn't say more direct air capture plants.
Well, I guess it's up to you to answer, but I mean, the fact that you can do something on the stage of meters doesn't mean, or on a scale of a machine that is this big, doesn't mean that you could do it on millions and trillions of tons, right? So we're talking about trillions of tons of emissions, so we're talking about something that's much, much, much bigger. And if you think about Tesla, they almost failed not because of the first car, but they failed in making 1 million cars. So making it big, that requires not just a smart institution like ETH, but it requires big investments and people who know the process engineering and who know the financial systems, and I'm not the right person to talk about this. But when I say infrastructure, I mean, we have to make it big, and you have to start early to make it big, because the learning, the economy of scale doesn't come from today to tomorrow. That takes a certain time.
Hi, Reto, it's Tony, Pat, we know each other. So I'm going to try to ask a science question. And for every ton of CO2 that we take out of the air, how much are we really taking out of the air? Because I assume a fair amount of the CO2 has actually entered the oceans. And so if we want to draw down the atmospheric concentration by a ton, how much do we have to take out of the air, realizing that part of that we take out of the air is going to be replaced by CO2 coming out of the oceans?
Oh, it's about the same airborne fraction that you have when you emit. So when you emit a ton, then about half of the ton of that ton goes into the ocean and the biosphere. So when you do the reverse, if you really want to extract 1 ton from the atmosphere, then you have to extract 2 tons because the rest is coming back up. So the same processes basically apply. But I think the way I think about it is you try to stop emitting, and whatever is left when you emit, you have to take it out somewhere, right? So 1 ton that you cannot avoid has to be taken out from somewhere else, and then your net zero will be there. Right?
So this is about net zero, right?
Yeah.
And to reach net zero, imagine the next 20 years, we need to put a price on carbon, right? So what price would this be from your perspective?
Well,
is
again,
it like $100?
Tony is the person to talk about policy instruments, but I mean, we are at $100 per ton in Switzerland. That has made some difference, but not necessarily, not nearly enough. So it's probably going to be somewhere between 200 and 300 or so. And if you talk to the Climeworks people, they say with $200 a ton, things are getting really, really interesting from a technological point of view. But maybe Tony wants to add something.
I can say from the policy research perspective, it's important to realize it's not just about the price on carbon. That a price on carbon can certainly help, but it's really a mixture of things. And so, for example, the price on carbon we're likely to get in the coming years will not be high enough to drive this technology unless we do an awful lot of other things. And in fact, many of the other things, support for the new technology, support for synthetic aviation fuel, stuff like that, may actually prove to be more important than the carbon price. So you can't say, oh, we need a carbon price of X. It's all about the whole mixture of things that you do.
Right.
Thanks, Tony. He's the expert on the policy instrument, so talk to him if you need more.
Thank you, Reto. It was amazing.
Thank you very much.
Ladies and gentlemen, this was a good start. Now we're going to switch to the US via our stream here. We switch to Director Uduak-Joe Ntuk. He's supervisor at the Division of Oil and Gas and Geothermal Resources at the California Department of Conservation and the California Government's Office. He is also professor of the California State University Long Beach for the Chemical Engineering Department. Professor Uduak-Joe Ntuk, we start the session now, so I would say play, and then we have Roger Aines, and we will have a discussion with them.
Hey, good afternoon, everyone. My name is Uduak-Joe Ntuk. I'm with the state of California. I want to thank you for having me today. It's a pleasure to be here virtually with everyone at the Direct Air Capture Summit in Zurich, Switzerland. I bring greetings from California Governor Gavin Newsom, from Natural Resources Secretary Wade Crowfoot, the Director's Office of Research and Planning, Kate Gordon, and our Department of Conservation Director, David Shabazian. They all say hello. I want to thank the summit organizers, officials, distinguished guests, ladies and gentlemen. Welcome to the summit. I want to give a special thank you to Anna and her team at Climeworks for all their hard work in organizing today's summit. And just want to thank all the attendees for taking time to participate, whether in person or if you're watching online. I'm here in Southern California. We're in the Pacific Standard Time Zone, so we're about 9 hours behind. It's 5:30 a.m. here on Tuesday morning, so it's a very good early morning here in the Golden State for me. We're coming off also a holiday weekend. It was Labor Day yesterday, which is our federal holiday where we celebrate the contribution of workers and the labor movement in our country. We're thankful for contributions of workers. They help make our nation exceptional. They help drive California's economy, which is the 7th largest in the world. And they're currently leading the fight against coronavirus here in the U.S. as frontline workers who are caring for our sick ones and loved ones, helping make sure that our grocery stores are stocked with food, and protecting us against wildfires and the medical coverage we need during the pandemic. So we really were thankful and celebrated all of our workers this weekend. We always knew there could be a pandemic, we just didn't know it was going to be right now. Today at this Direct Air Capture Summit, I'm going to talk about 3 main things. My regulatory agency's new name change and mission. We're going to talk a little bit about California's climate change goals and to become carbon neutral by 2045, and summarize 2 pilot projects that are happening here in California. But first, let me introduce myself. I'm Uduak-Joe Ntuk, State Oil and Gas Supervisor. I'm the 17th State Oil and Gas Supervisor in California history. I run an organization called CalGEM, California Geologic Energy Management Division. It's actually been around 105 years. Formerly was called the Division of Oil and Gas and Geothermal Resources, DOGGR, but we got renamed this year. Governor Newsom signed a bill, AB 1057, last fall that renamed our organization. My background is in engineering, environmental policy, government administration, and climate change. Prior to coming to state service, I worked for Los Angeles Mayor Eric Garcetti in the 2nd largest city in America, LA. I was the city's petroleum administrator, where I oversaw petroleum refineries, pipeline franchise agreements, and the urban oil and gas drilling sites. I previously worked for 3 Fortune 500 companies before I started my career in the public sector. As far as academically, my background is I have a bachelor's degree in chemical engineering with a minor in business, and I did my master's degree in petroleum engineering with a focus on smart oil field technologies, also known as digital oil fields of the future. I was personally trained by Vice President Al Gore on climate science as part of the Climate Reality Project from the Inconvenient Truth documentary. I'm also a former Green for All Fellow with the organization founded by Van Jones, and completed a sustainability fellowship along London Business School. So my full biography is in the slide, or you can see it online. I want to just say this new bill, AB 1057, the governor signed last year, that added explicitly advancing the state's clean energy goals for us to mitigate greenhouse gases from our regulated entities and have a focus on public health, has moved us from being, I would say, part of the problem to now being part of the solution. Our mission includes advancing California's goals of becoming carbon neutral by 2045, responsibly managing our oil and gas production and oversight and regulation. And we do it with a center on public health and safety on all operations. We're conducting a new public health rulemaking effort. We're focused on mitigating greenhouse gases, transitioning to zero emission vehicles for the state, and finding other ways to have cleaner energy source production. But we're doing this with a science-based, data-based approach founded in sound engineering practices that oversees all the regulations that we do for drilling, operations, and the permanent closure of energy wells. But we also do pipelines and facilities associated with these operations. And so we do witnessing, inspections, and other types of regulatory activity. So we have 4 districts across the state, northern, coastal, and southern. They each have a regional office. We have about 300 employees statewide and about a $100 million budget. Next talk about our regulated entities. CalGEM regulates 3 core energy infrastructure areas within the state. Conventional oil and gas production, the geothermal energy operations, and then the underground natural gas facilities. So first, just talking about oil and gas production. CalGEM has historically, and from our beginning, has overseen oil and gas production in California. So that's drilling, operations, plugging and abandonment of wells. And we're focused on doing that to protect public health, safety, and the environment. California is the 7th largest oil producing state in America. However, we had our peak oil production in 1985 and has been declining for the last 35 years. We are currently at the lowest level of oil and gas production in modern state history, producing about 400,000 barrels a day. Last year in 2019, we produced about 161 million cumulative barrels of oil in the statewide. So today, California has a fundamental shift in how we regulate and oversee oil and gas. We now issue more permits to plug and abandon wells than permits to drill wells. This has changed in the last few years under the Newsom administration, and it will continue to be this way for time to come. We also oversee geothermal production operations. The United States is the largest producer of geothermal energy in the world, and California is a leader in the country with the most production. We are on the Pacific Ring of Fire with the tectonic plates that give us a unique geology to have a large amount of geothermal. So we have the largest capacity in the country, and that's really set us apart. And geothermal has been able to provide us with clean, renewable energy source to support our grid, and also helps us advance towards our 2045 carbon neutrality goals. Again, we regulate the operations, maintenance, and drilling and closure of geothermal wells across the state, both on public and private lands. In 2019, California generated about 11,000 gigawatts of geothermal electricity, which was about 5.5% of the state's energy portfolio. There's 43 operating geothermal power plants in California with about 2,700 megawatts of electrical power. Geothermal energy provides baseload power. It can balance the state's electrical grid, especially when you have variable sources of like wind and solar, that can come in and fill in when they're not able to do it. So, and it helps us prevent using fossil fuel facilities which may emit toxic air emissions or climate damaging greenhouse gases when we have geothermal power plants. There's more than 650 active high temperature wells in the state, and they cover a large geographic area. We actually have the world's largest geothermal complex, the geysers, with over 22 geothermal plants located north of San Francisco. But we span all the way down to the Mexican border in Imperial County, where we also have geothermal operations. And we are currently looking to expand geothermal operations and combine it with direct air capture. And so we're looking at that, and we're also looking at new strategic minerals like the lithium to add to the geothermal value chain. Thirdly, we have underground natural gas storage facilities. We have the strictest underground gas storage regulations in the nation. Natural gas is currently used as an energy source for a variety of purposes, powering electric power plants, heating and cooking for residential and commercial buildings, and is very widely used. In California, underground gas storage is an injection of natural gas, which is predominantly methane, into wells into geological formations, sometimes 1 to 2 miles deep in the earth. The purpose of it is to store natural gas at off-peak times and be able to use it when demand is high. We have 12 facilities in California, 4 in Southern California, 7 in Northern California, and 1 in Central California. all these facilities are in depleted oil fields where they pump the natural gas in. So we regulate the well construction, the well testing, the risk assessments for all the wells and associated facilities at the underground gas storage facilities. Next, I'd like to talk about California's climate change goals. You may be very familiar with AB 32 in 2006 that required California to reduce greenhouse gas emissions below 1990 levels in 2020, a reduction of 15% emissions below the business as usual case. This was really the founding of the beginning of our current trajectory on addressing climate change. And it was built into our scoping plan by the Air Resource Board, encouraging local governments to adopt goals to reduce greenhouse gas emissions also below 1990 levels. And we've been very successful. Actually, in 2020, we reached our to get to the same level as 1990 statewide. We did a little bit ahead of time. In 2016, California adopted SB 32, setting a 2030 goal of 40% emission reductions. And that was two big, bold goals in 2018 to say 2045 was going to be when the state would reach carbon neutrality. And it set for 100% carbon emission-free electricity generation. And so we continue to make progress. This is arguably the most ambitious climate policy in the country, if not the world, and we are working to implement these regulations and laws dutifully. Next, I want to talk about a couple of pilot projects we have in California. We're going to get more context about carbon removal, particularly direct air capture from my fellow Californian, Dr. Roger Aines, who is the next session. But let me talk about two projects that are happening. First, it's a Climeworks direct air capture pilot project. They've applied for a federal grant this past May to do some novel or some initial research of direct air capture for carbon dioxide directly out of the atmosphere. That's about a $2.5 million grant for 3 years. It's trying some new sorbent materials. It's specifically trying to get some operational data and then build the foundation for a larger scale deployment in the near future. The proposed technical approach is to construct and operate an integrated direct air capture system, fielding and testing novel combination of Climeworks direct air capture process and hardware with a transformational structure absorbent. So they're going to be doing field testing, and they're still doing site selection as they're waiting for the federal government to respond. The other project that's related is the Clean Energy Solutions. This is in Central California, Mendota. We call a Class 6 well. This is regulated by the United States Environmental Protection Agency under the Underground Injection Control, US EPA UIC projects. They've actually submitted for the first well in California history to be drilled to permanently store CO2 in the ground. It's about 9,000 feet in depth. It's going to inject about 350,000 tons of CO2 a year for a 20-year time period. This is for permanent underground storage. This would qualify for what we have the low carbon fuel standard credit, and then we also have the 45Q federal tax credit. So we have unique economic incentives in California to do some of these. And so the goal is to have a carbon capture and storage for sequestration, so they call CCUS. And this is the first time we're doing this in California. And they're going to try to do a carbon negative energy with a gasified waste and biofuel, and they're going to have syngas. So basically have a biomass power plant where they capture the CO2. They're going to have a well on site at the facility where they directly inject it into the ground. This is new. We're working with them, Clean Energy Solutions. Their consultant is Schlumberger, who's helping do site characterization and waiting for the US EPA to approve this first permit that's coming. Just in closing, California has a long history of being a national and global leader in climate change and greenhouse gas reductions for the last several decades. Governor Newsom is leading the state to take bold action to address climate change and meet our 2030 and 2045 goals. CalGEM is working to continue California's leadership in this space through robust oversight, regulatory activities, evaluating multiple pilot projects. The two I spoke about are two of probably a dozen that are going on in the state right now around carbon capture, use, and storage. And it's going to really help us reach our carbon neutrality goals. We have to have negative carbon emissions to reach our greenhouse gas and climate change goals. And so we're looking to do something new and bold. You know, we have a pledge to the California dream. We know that our future is interdependent and we need to work together. We talk about a California for all, where no one's left behind. And we're really looking to work together with everyone to address our common challenge. California has been and will continue to be a leader on climate change. We know our future depends on it. We have a tradition in California about prosperity and progress. And as we recover for the coronavirus pandemic, we know that we can rebound together. So there's a lot of big choices we need to make in the near future, both as nation states, as international players, multilateral, bilateral agreements. But we know the health of our planet is at stake, and literally millions, if not billions of people's lives around the world will depend on the outcome of our decisions. I want to thank you for your time today. Thank you for the invitation to speak, and welcome to the Direct Air Capture Summit. My name is Uduak-Joe Ntuk, and I'm going to pass the baton to our next speaker. Thanks again for having me.
This was Professor Uduak-Joe Ntuk. I just wanted to say you don't need to applaud because he was recorded. Anyway, but our next speaker is live and remote from California. Very interesting for me. He's already there, Professor Roger Aines. And Dr. Roger Aines, hello. And for me, California is always very exciting because as a futurist, I love to look to California. It's the epicenter for emerging technology, epicenter for also bringing science to business. And we are very, very happy to be here with you. You are from the Lawrence Livermore National Laboratory.
Yes.
And you will present about the California and the climate roadmap. I'm so happy that the connection works so well. So just go ahead, welcome, and we are listening to you now.
Okay, thank you very much. And I wish I was there with you, but this is second best. As you can see, it's very early in the morning here, but delighted to be here. So I'm going to go dark for just a second while I start up the screen share, but I will keep talking to you while we do that, and then we'll be back in just a second. Okay, so while this loads up, I'm Roger Aines. I'm the Chief Scientist of the Energy Program at Lawrence Livermore National Lab, which is one of our big federal research facilities. And at our lab, for the last 4 years, we've had a big program in trying to understand what negative emissions really are. You've seen the plots from the IPCC, you've seen a lot of people talking about things, you think about trees, about BECCS, and the issue we looked at was, like, how real are these things? How much difference can they make? And in particular, how can we get business to work on this? Because you don't move billions of tons of anything without businesses that make money. So we launched an initiative to try and understand this. And one of the very first things we did was to look at California's case. And just as Uduak-Joe described, how can we reach these very aggressive goals? So Director Uduak-Joe showed you the overall goal here, and the official laws that we have get us to this goal in 2045 or 2050 of 86 million tons of emissions. But now we have a new goal, just as many progressive organizations do around the world, of getting to zero. And we assessed that we were going to need negative emissions, and we assessed we need about 125 million tons a year of negative emissions in order to reach the goal of net zero by 2045. Now, this is an approximate number. Obviously, if we overshoot, that's good for everybody. But that's where we got the goal of 125 million tons. So what we set out to do in our analysis was to say, how can we actually do this? What are the things that are real to get this number? But we restricted ourselves to an important thing. We said we have to do it inside the borders of California, because it's really really easy to imagine that some other country is going to do it for you, or in our case of the United States, some other state's going to do something, you're going to buy it from them. But we said, no, let's just stick to the rules of we'll do it ourselves. So these are all things that we could do inside the state of California. And we considered all the usual technologies that you think about when you think about negative emissions. The ones with check marks were included in our report. Over on the right, there are several that we did not consider, mainly because we didn't have costs that were good enough. All the other ones, we had approximate costs, so we could say, how much would it actually cost to do this at full scale in the future? And so we didn't consider mineral weathering, even though it's a favorite of mine, and we didn't consider ocean issues either. And this is the major takeaway that we got. There are 3 categories that California could use to reach 125 million tons a year and to reach net zero. The first is natural and working lands. You heard our first speaker talk about the fact that trees are maybe not as big an answer as some people would like them to be. Well, we said, let's look at it in detail. Exactly how much can we do in California with our forests and our wetlands and our soils, consider all these natural solutions. And the answer is, even being very aggressive, being very optimistic, we could get about 25 million tons of negative emissions per year. So it's good, it's inexpensive, we absolutely want to do it, it's good for the rest of the climate, but it's not going to get us 125 million tons. It's not going to get us our net zero. So the next thing that came into play is the thing that you heard from Director Uduak-Joe about biomass with negative emissions. And we don't call this BECCS because we generally tend to think that electricity is going to be well handled by renewables, and so we tend to think about fuels. And so it turns out that in California, there's a lot that can be done there because we have a lot of biomass. We have 53 million tons a year of waste biomass in California that includes the forest material you see being cleared here to try and reduce our fires, which I wish we had done sooner, as I sit under a pall of smoke here in Livermore. That can be a big contributor, and this is all waste material. This is all trash, agricultural waste, and forest waste, things that are already being created. No new agricultural products required to reach that level. A lot of new construction required to get there. And last is direct air capture. So why is that last? Well, it's the most expensive today, as you know. We have hopes that it will be less expensive in the future, but I think it will always be a little more expensive than these other 2 options. And so it's going to be the thing that we use to fill in our goals, the thing that we use to fill in our aspirations. And all of these are available at some scale today, so we can make estimates of their costs. And when we do that, we get this cumulative distribution plot. And we estimate that we could do the entire job, the entire 125 million tons in 2045 for about $8 billion per year. That's an important number. Might sound like a lot of money, but California is a big place. That's about 0.3% of our GDP in California. It's about 1/3 of what we spend managing trash in the state of California. So it's not a huge number. And you see that natural solutions, the trees and wetlands, are the least expensive, so we'd start with those, 25 million tons. The next in orange, you see all of the biomass-based options, and it turns out that making hydrogen out of biomass is an extremely important thing to consider, mainly because the hydrogen is valuable, so that reduces the overall cost of removing the CO2. What you see here is the price that's left over, the price that you have to pay for the CO2 after you already get paid for the hydrogen. And of course, when you convert biomass into hydrogen, you get all of the CO2 back and you can store it underground permanently, and you've removed CO2 from the atmosphere by doing that. The last thing to the right, the 2 bars, are direct air capture, and I'll talk to you a little bit at the end about how we estimated costs for California. These are California-specific costs in 2045. Whole thing, $8 billion, makes a lot of sense, a lot of stuff to build, but it's very possible to do. And of course, there's a lot of other options about varying one thing or the other, and all of these things work out pretty well, and that's a good news, is that with all of the options you saw on that last chart, there's a lot of ways that policymakers can choose to do things. We can emphasize hydrogen, we can emphasize direct air capture, we can emphasize transportation fuels, and they all work. They require natural systems, they require permanent storage, but they provide a lot of value. And we mix and match all of those different options The most expensive one that we could get to is about $15 billion a year. So this means that negative emissions will work in California. And California is like a lot of other municipalities, or not municipalities, but regions, in that it has agriculture, it has waste material from cities, it has geologic storage, it has all the things that you need to do the job. But it has something really unusual around the world, and that is a thing called a low carbon fuel standard. And it's basically a policy means for reducing the emissions from transportation. And it does so by, it's fundamentally a cap and trade system on the carbon intensity of carbon fuels. And today, that price trades in terms of tons of CO2 avoided. It's a privately traded system. The parties who have to meet the cap have to buy them from those who have exceeded the cap. Trades for about $200 a ton. Now, as we just heard, that's a number that starts to get some significant action. And in California, today, direct air capture counts for that. It's as if the car emitted the CO2 and later you captured it. They consider that to be fun. And if you do that and put the CO2 underground, it has to include geologic storage, direct air capture is counted in our low carbon fuel standard. Nobody's doing it yet. I hope that all of you will start in the near future. So I want to talk a little bit about how we meet this entire system cost and sort of what the basis of those estimates that I just showed you are. I'm not going to talk about construction and operation. You have experts in the room that can tell you about direct air capture much better than I can. But I'm going to talk about some things that are important: energy supply, learning, and transport and storage. We have to consider all of these things together when we look at the system cost. And that cumulative distribution cost curve I showed you considered all of these things for each of those technologies. Important thing is that the CO2 is going to have to go underground. There's just not enough places to put it above ground. We'd like to make things out of it, but there's just not enough to make. The amounts of CO2 we're talking about will have to go underground. This is good news. We had an oil industry in California. As you heard, it's declining. The good news is storage can now increase. And we did a detailed study of where we can put it. And in these two boxes that you see highlighted in brown, we evaluated some of the important oil and gas fields in the state because we know the geology there. It's not that we're going to put the CO2 directly in the oil and gas fields, but into the rocks around them. And when we evaluated these, we found that California has great geologic storage. There's plenty of room. Just in these two areas, we could store 17 billion tons of CO2 safely. So we feel like California is very fortunate. We have the rocks to store the CO2. It's near the places where we may need to generate the CO2. And so I want to talk about direct air capture and how that fits into it. And of course, direct air capture is mostly, the energy required is mostly heat. And so we have to think about the energy in terms of heat, and we have to think about the land use that it needs in terms of both the supply of heat and the contactors themselves. And one of our important learnings is that land area, especially for the energy, may be the primary limit on where we display these things. We're going to need, because of that, we need concentrated energy sources if we can get them, like geothermal. And we've all logged the idea of the plant that you're sitting very near there that Climeworks operates, uses waste energy. We evaluated that in California. There's just not enough waste energy. The fact of the matter is, whenever people start talking about waste, it means that they've done something inefficiently and they're going to be trying to do it more efficiently. So there just isn't that much waste heat around to get the kinds of large levels that we need. And so we always think of doing these things with solar. This is the biggest solar plant in California. It covers about 20 square kilometers. As you see, it's not actually contiguous panels, so I'm covering the entire area. And if we wanted to run direct air capture systems off this, we'd need one system this size to capture about 1 million tons per year of total carbon dioxide. These are analyses by Jennifer Wilcox from the University of Pennsylvania. And so if we do it, our air capture with solar photovoltaics, we're going to take an enormous amount of land, and that matters everywhere. You sit in Switzerland, you understand this perfectly well. We have the same constraints in California. We have many empty spaces, but we love our empty spaces. We don't want to commit them all to solar panels. And so having concentrated sources, for instance, using natural gas, which might sound like anathema at a direct air capture conference, but the trick is If you use natural gas, you capture all the CO2 that you generate. But geothermal is also a terrific way to power these systems. Learning is very important. We all worried about the cost, and you're about to hear some pretty optimistic estimates. I'll be willing to bet you from the following 3 talks. So we looked at this independently. We said, just using our own rules for learning rules, how much should we expect the cost of direct air capture to decrease? And there's 2 ways to power them. One are 2 systems, that basically the sorbent system, the kind of thing that Climeworks develops, and then solvent systems. And these have different learning rates because they're different size systems, but average learning rates for technology are between 5 and 20%. So we just said, well, okay, we'll take a 15% learning rate for sorbent systems because they're small and you can build more of them. Your doubling rate is faster. But we had assumed a smaller 10% learning rate for solvent systems because they're large and you can't build as many of them. And as you see, the early on costs are high, but when you build enough of these things, the costs drop down to the level where our $200 per ton current value in California is going to get you within the range. The important thing is to get those early systems built, and that's where government support is going to be so important. Transportation is also a big cost. We evaluated 3 different ways of transporting CO2. You can move it by pipeline. That's great. Everybody always wants a pipeline, but let's face it, pipelines are hard. So we also looked at truck and rail, and it turns out that for very small systems or for small distances, truck is great. Truck is not that expensive. Rail is even better. Moving unit trains of CO2, or we're replacing the unit trains of coal in California with unit trains of CO2 maybe. Like to see that. And pipelines, obviously, at longer distances are always going to be less expensive. But the fact is that either one of these things provides only, at most, maybe $10 per ton of total cost. So transport is not a big deal. The hardest thing is probably building these systems. Just like with the energy system, it's not the cost, it's the other implications of building these things that we have to deal with. We build a center trunk line in California that goes up and down the Central Valley following the existing gas pipelines. We'd be able to collect CO2 from a number of sources, including direct air capture systems, which we'd like to build in 2 places. One in the Salton Sea, down the far south of the state, where there's available geothermal power. And then in the center of the state, in what you see is Kern County, which is where much of our oil production comes from today. And the good news about that place is that's also a place where good geologic storage exists. So you could extract natural gas, use it to power these systems, put the CO2 all entirely back underground in those places. So I've tried to highlight for you some of the details of how we calculated how California could get to a net neutral economy in 2045. And in fact, one of our other findings is they could get there faster. We could get there by 2035 if we wanted to. If you wanted to make the investments, there's nothing in there that's fundamentally time constrained. The technology mix has relatively minor impacts. You could do it a lot of different ways. That means policymakers have a lot of choices because when you spend this amount of money, you also want to obtain other value, jobs, development, environmental impacts. There are things you have to consider besides just the cost. Geologic storage is extremely important, and direct air capture is going to be important in any scenario. You're going to always need it to polish off the other things that either are more expensive or don't do as much as you would like them to do, like trees, frankly, aren't going to be as valuable as we might like them to be. If you want to get more details, if you just Google the Getting to Neutral, you'll find our report. And with that, I look forward to answering questions. Thank you very much.
Roger, this was your applause. It was an amazing overview of all the technologies and puzzle pieces we need to get together to become carbon neutral. I was wondering, 2045 was all the tipping points we're seeing now, like permafrost, Greenland ice, also the wildfires you are now experiencing. Could we speed up a little bit?
We'd love to. I think it makes sense to start talking about doing this. And this is one of the great debates, of course, which occurs. People say, wait a minute, we should spend the money eliminating emissions today. We should, absolutely. And we have to have negative emissions as well. And we should start those as soon as possible. And unfortunately, some industries tend to think of negative emissions as an apology for continuing to emit carbon. That's not acceptable. We have to stop emitting carbon dioxide, and we have to remove it from the atmosphere today.
Next week we are in Copenhagen, and Copenhagen says they want to be carbon neutral in 2025 already. So what roles can cities play in becoming carbon neutral and pushing carbon dioxide removal forward?
Cities have two really important functions here. The first is trash. Enormous amount of biomass leaves cities in trash. Today it either goes into landfills, many places it's incinerated. In Oslo, they're now building a demonstration plant to burn that CO2, make electricity, and capture the CO2 and put it underground. That's a really important negative emission that all cities have available to them. The second is the natural gas that they use today. In Denmark, almost all the natural gas comes from biogenic sources. They have a lot of cows, they can do that. But when you capture the CO2 that's generated also from making that methane, you can have negative emissions associated with your natural gas. So those are two things that cities can do.
So in California, you now really experience the power of climate change with all the wildfires, and you had like 54 degree in Death Valley, I think.
Yes.
That's amazing. Huh? So how does
it was 45 degrees here yesterday.
How does this inform your work on carbon dioxide removal? How does this change in the last weeks and months? Do you feel more pressure from governments and cities?
You do. There's no argument about climate change in California. The government's ready to act. The citizenry are ready to act. And a lot of the question is, what do we do first? Where do we invest? Unfortunately, COVID has really stopped the state's ability to invest in these large projects. We're broke. We don't have the money to do it. And unlike a federal government, we can't print new money. So we're hoping that our federal government will come around to investing in these things, because the enormous amount of capital investment that's required here has to be provided from private sources, from public sources, but it's not going to come from state government, unfortunately, today.
Thank you. Roger, to the audience, last question to the audience, okay?
Okay.
It's early in the morning, so you have some more time for us, right?
Oh, yes, absolutely. I've had my coffee. I'm ready.
You're ready for breakfast, huh?
Yes.
So, any questions from the audience? Please.
It's Christoph Beutler from Climeworks. Thank you so much, Roger. And as I've said before, this is an amazing report, and it's really illustrative. Can I just ask, it suggests to me that you could also go net negative with the methodology you have shown in this report. Is that a correct assumption?
Absolutely.
Thank you.
Roger, we want to say thank you. It was a brilliant presentation. We really had a good connection with you. So enjoy the rest of the day. Next time, hopefully, we meet you in Zurich.
I look forward to it.
Bye-bye.
Bye-bye.
Now, before we go to the coffee break, I want to open up the highlight session of today. We will have all the leading DAC companies here. We will have Climeworks, Global Thermostat, and Carbon Engineering together in one session with one panel. You can ask Q&A. So please first welcome with me Christoph and Jan, the founders of Climeworks, on stage. They will start. Christoph, you will start, actually. And then we will invite the others to the panel and the presentation. Christoph, stage is yours.
Thank you, Niels. Well, I'm happy to welcome you to the Climeworks presentation. After the introductory speeches, it will be very simple for me to explain why direct air capture is needed. We understand that in order to achieve climate targets, we have to get to zero as fast as possible, and thereafter realize substantial negative emissions. The role Climeworks is playing in that context is that in this first journey to zero, we are addressing unavoidable emissions. For example, the emissions, the remaining emissions of an electric car, or as Reto said very beautifully in the beginning, also flights, quite controversial topic, as unavoidable. And thereafter, of course, we want to realize substantial negative emissions. Well, since today, 3 direct air capture companies will be giving a presentation, let me share a couple of points, what is characteristic about Climeworks. First, on the technological side, we're following a modular approach. Here you can see, as an example, a photo of our modular CO2 collector. The modular approach has a couple of implications. First, we do understand and operate already today the largest repeating unit of our system. And second, we are approaching the scale-up challenge not through making our units bigger, but through rather mass production or volume production. Another technology aspect is, we talked about energy, Roger just outlined that very nicely. A key requirement for direct air capture is energy, and the key question is, where does this energy come from? The beauty about our system is that a large share of our energy consumption comes from heat at 100 degrees Celsius. We refer to that as low temperature heat, and that heat can be easily provided by renewable energy sources. And that, well, as Roger mentioned, natural gas as an energy source, we as Climeworks commit to sustainable energy sources as the energy source. Hand in hand with that, we do have a low carbon, low life cycle impact of our technology of smaller than 10%, meaning that for 1,000 kilograms of CO2 we're taking from the air, we're only emitting less than 100 kilograms of CO2 back to the atmosphere. And finally, on the business perspective, we're the first company that is offering direct air capture solutions to the market. Well, many might wonder, how does that actually work? Here you can see a schematic of our modular CO2 collector, which is filled with granules. And in a first step of our CO2 capture process, we stream air through this modular collector, and the CO2 contained in the air sticks to the surface of those granules. After some time, those granules are saturated, or the surface of those granules is saturated with CO2. And in a second step, we close this modular unit and we heat it to 100 degrees Celsius, and thereby the CO2 from the surface is released again back to the gas phase, and we can pump it out of the system as a high purity gas. The big question is, what are we doing with this high purity gas? At Climeworks, we're committing to pure removal. What do we mean with that? We mean permanently storing the CO2 underground. Later, there will be a speech by our partners Carbfix, by Edda. They will explain that in much more detail. Here, just briefly explain how we are generating carbon dioxide removal with our direct air capture technology. We do have a plant in Iceland, which is installed next to one of the largest geothermal facilities. And from that facility, we're receiving renewable energy to power our plant. You all know, with this energy now, we are capable of getting the CO2 in high purity form. We're mixing it with water, pumping it underground into very porous rock, which is called basalt. And at the conditions we do have in Iceland at the specific site, the surface of the rock subsequently reacts with the CO2 contained in the water, and literally the CO2 is turned into stone and in such removed permanently from the atmosphere, which actually is a market need which we discovered, and that brings me to our products. I mentioned that we are the first company with a direct air capture solution on the market. What is our solution? We do have products for you and me as people that are Climeworks carbon dioxide removal subscriptions. We have some standard module or standard offerings. They can be like from 7 euros to 49 euros, can be customized up to 2,000 euros. And our promise is, corresponding to the plan you're choosing, we are removing the respective amount of CO2 from the air and provide it for underground storage. We also have offerings for companies. On the company side, we're offering carbon dioxide removal as a service, as we call it. Also there, we're seeing that companies are using this service, for example, for their employees as a benefit in kind. Or companies can use that for their own emissions, or the emissions of their products. And I'm very happy that we can share already 2 agreements which are out there. You might have heard of the payment provider Stripe, who contracted Climeworks to remove carbon from the air. And just yesterday was an announcement by car maker Audi that they contract us to remove carbon from the air in order to address the emissions of their business. Well, in order to be able to remove carbon and offer such products, it's of course very important to have a capacity backbone, so to have a DAC backbone connected to storage options, and that is what Jan will now explain in more detail.
Yes, so talking about the next steps and about scaling up. So as the previous speaker, Roger, nicely pointed out, there are a couple of challenges when you talk about direct air capture. There is a cost question. We always debate the cost question. I think in the meantime, there is quite a good alignment between the different developers of technology that the ranges that have been shown before, something like $100 to $200 per ton, that is something reachable, and someone recently nicely said between today and $100 per ton, there are just humans, so there is no physical law why this is not possible. There is a challenge of energy, and then there is a challenge of learning, and I would like to focus on the latter one, on scaling up and how we address that. So if we listen to science, a number where we should get by mid of the century is something like 10 to 15 billion of tons of carbon removal. And let's assume for a moment, for an order of magnitude, that this is to be done by direct air capture. So if we look where we stand today, at roughly about 1,000 tons of CO2 captured per year, which is installed in the field, which is on the market. So that's a factor of about 10 million of scaling and of learning that we need to overcome as an industry. And now, how do we address that as a company? Going over here, we've been working on that since 10 years. Since 2014, we have the first generations, or we had the first generation of a CO2 capture plant in place. And during all that time, when thinking about scaling up, in our philosophy, we were focusing on 3 principles. The first principle is that of fast iteration and fast learning thereby. The second principle is learning in the field, so learning with customers, learning with our plants. And the third principle is that we always tried to develop the tech, to develop the scale-up at the same pace, in parallel, and at the same time with developing the market. Well, what does that mean concretely? So you see a SketchUp or a line out of a roadmap over, like starting in 2014, where we built the first prototype of a system of today's Climeworks technical concept. We were working in roughly 3-year intervals of developing, and then launching and implementing a new generation. So that was 2014, 2017, and today, happy to announce what happens in 2020. We built about 14 plants over the last years, some of them very small, others larger, as those you know from the pictures. And that also means that we can move from step to step with quite reasonable amounts or volumes of funding required. So starting in the past, we were able to move with something like 5 million to a next step now, thinking about the next plant we're building now, that is something between 10 and 20 million dollars that we need for that. Thinking of a next step, we are thinking of 50 to 100 million, so we can grow these the amount of funding required together with the business in a quite linear and reasonably achievable way. Concretely, our first plant, and that was the biggest point in time for Climeworks, that was back in 2017, the first commercial plant that was launched. You see the picture here, most of you will know it. And what did we do at the same time? We contracted a greenhouse, we later expanded the plant, and we contracted a beverage bottler. And today, like in the framework of getting that technology, on that technology generation out there. As an example, we also became a certified and audited supplier to the Coca-Cola company. So we combined that with an important market step, bringing our company from a standards perspective, from an audited perspective to a next level. Then last week, we announced for the first time the next step, and I'll show some more pictures in a minute. What happened since then? Quite a bit of technology change. If you look at the pictures, you see these containers look differently, so there was put a lot of development effort in that step. A decent scale-up from 1 kiloton per year to 4 kilotons per year. A new application, combining direct air capture with storage on a commercial scale, and bringing us to a level where we use this plant to enable a further scale-up. Like, this is in execution. This plant is being built as I speak here. The largest portion of our team currently, of our development team, is now focusing already on the next generation, which again is targeted at a roughly 3-year interval for 2023, where you see a image here, where the main topic will be scale-up of more or less known technology. There the scale-up factor will be between 10 and 20x, as opposed to the 4x for the current step we are doing. And the main benefit will result from a larger plant. So making things bigger reduces a lot of costs, which are so-called parasitic costs, which are one-off costs, which you just have to pay no matter how big the plant is. And then thinking at another 2 to 3 year horizon, roughly in 2025, towards a rollout out towards a megaton scale removal. That will then be a multiplication of these units, which is then mainly triggered by mass production of individual components, such as the CO2 collector containers. And very importantly, another element to enable each of the steps is, and I mentioned that before, is the market, are our customers, which can be private pioneers, which can be corporate pioneers, or, as we learned before, governments. We built the first plant after having signed a contract, an offtake agreement with our customers, a greenhouse, a beverage company, to take the CO2 from there. Last year, we launched our first product to private people, to individuals, and we started talking to many corporates who were trying to achieve their climate targets and were looking for real carbon removal or permanent and long-term carbon removal solutions. So we were able to close contracts, as Christoph has mentioned, to engage private pioneers. We have more than 2,000 people purchasing subscriptions from Climeworks currently, which then unlocked the investment into the Orca plant, and where we are currently working on is talking to more corporate customers, to more privates, and on the politics side. And one major goal is to unlock, as soon as possible, the investment into a next generation plant. And to do that, we are now talking about serious finance volumes, having pioneers and having committed parties that are committed to be part of the capacity of this plant for a time period of something like 10 years is a vital element. Now, zooming in a little bit, just to give you an outlook of what is coming towards the end of this year, a couple of pictures from our current plant that is being built in Iceland. We call it the Orca plant. On the left-hand side, you see a computer image of the installed plant. Up there in Iceland, you see there's a new optimized collector, new design. The capacity is roughly 4,000 tons per year, so that is 500 per container, so that's at least a 2x from where we stand now, so that's in numbers, the optimization. We are investing more than 10 million into this project, and it will be located, and you see it in the middle picture, at the Hellisheiði power plant in the vicinity of Reykjavik in Iceland. We have contracts on the one hand side with the local utility company, On Power, which is a subsidiary of Reykjavik Energy, supplying us with geothermal heat and geothermal electricity. And on the other hand, our partners are Carbfix, and we'll hear also more details about that later, who are injecting the CO2 into the basalt rocks to turn it into stone and permanently store it underground. On the right-hand side, you see one of the containers, so those are all manufactured in the meantime. You see them in fabrication, and the current Timeline tells us that in Q1 2021, the plant will start operation, and we calculate with a lifetime of about 10 years, which is rather to be seen as an economic lifetime than a physical lifetime, which could potentially be much longer. And with that, finishing up with a couple of latest pictures from the construction site. You see it in nice and Icelandic summer weather, pictures from August, where the first piles are being rammed into the ground. So this is how it currently looks like, and within the next couple of months is going to turn into what you've seen here on the left-hand side. Thank you very much.
One question to you, Jan, and also Christoph. You are working in the direct air capture since around 10 years. You started working 10 years ago. And now it's so much about timing, right? So the next 10 years will be like crucial until 2030. You talked about your global rollout in 2025. What is a good timing for investors and like big corporates like German DAX companies to support you in scale up, to support you with investments from both perspectives? As a big company, as an investor, what's a good timing to jump in? And also, what do you need?
Yeah, well,
both of you.
I think what we've always said in the last months, really, out of 10 years of Climeworks, probably the last 12 months or 18 months were really the most crazy ones, starting with, like initially with the Paris Agreement. That's when it kick-started. A lot of things have changed. So 5 years ago, we would be talking to corporate sustainability departments with a small budget, with the idea to try and do something. Today, we are talking to many corporates on the one hand, where achieving climate targets is on the agenda of the CEO. And we have private people who are following us. And getting to your question, I think now is really the moment where we are, like, we have a very concrete scale-up roadmap. We have a very concrete series of steps when capacity can be laid out, and we are relying now on people bindingly joining us and saying, hey, we are off-taking the carbon removal. We are using that to achieve our carbon goals, and that will enable us to finance those plans, because it is not something anymore we can finance out of the pocket. It's real infrastructure investments.
You can help companies and governments to become carbon negative, but what if you talk about a global rollout? You need like millions of tech contractors. Do you have partners for this to do this global rollout, or who's doing this production?
Yes, so on the implementation side, that is a main focus. We are currently focusing on building up a network of partners who help us with the implementation. So Climeworks will not be a large EPC company building millions of plants. We have certain core components that we're building, but there are many industries who have done that over the past decades. Yeah. There are industries who know how to build up millions of tons, or put millions of tons of steel and concrete into the ground, and that is something we will do together with this industry that is existing, basically.
All right, so you're partnering with them.
Yes.
Could be like a German car manufacturing, like building negative emission cars.
As an example.
I would like to see this. Thank you so much. It was amazing. Thank you for the overview. Thank you.
Thank you, Neil.
Now, ladies and gentlemen, we switch to Canada remotely. We will have Jeffrey Holmes from Carbon Engineering with us in the session. Jeff has also worked on carbon direct air capture since 2008 already, both as an academic capacity and at Carbon Engineering. Jeff has led much of the Carbon Engineering's air contractor research and design projects. So, Jeff, we are very much looking forward to your talk. Welcome to the session.
Thank you very much. I guess I show my slides from my desk here. You guys will have to bear with me. This is my first Zoom presentation to a summit. Okay, so look, thanks to our friends at Climeworks, thanks to everybody who has helped organize this summit. It's wonderful to get so many people together who are interested in direct air capture and carbon removal. And this is, of course, one we were hoping to do in person, but 2020 took us by surprise as well. So as a company, Carbon Engineering was founded back in 2009. So I've had the pleasure of knowing both Christoph and Jan and their growing teams for over a decade. And we've been really impressed with the remarkable work that they've been doing to bring direct air capture to market. And we've been on our own development journey to develop a slightly different technology and come to market through a different path. But there's a lot of shared history and a lot of shared challenges that our two companies have been through over the last decade. So I think what I would say in the way of general remarks is that as a company, our goal has always been to develop and then to commercialize very large scale direct air capture technology. We think that carbon removal and air capture with sequestration as a way to achieve it is one of the really critical tools that we're going to need to tackle the climate challenge. So I'd very much echo what Jan was saying about the last 12 to 8 months being the craziest, but I would say also the best, because we're really starting to see a lot of corporate interest and individual interest. We're seeing governments start to devote more funding towards air capture and carbon removal, and we're seeing some encouraging signs on the policy realm as well. So in our opinion, what really needs to happen next for direct air capture is that collectively we need to move to very large scale deployment. Climate is a problem simply because it's large, simply because there's large volumes of emissions building up in our atmosphere.
Jeff, sorry to interrupt you. It's very, very insight and fruitful, but you wanted to share your slides, right?
I will do, yes.
Okay.
Just a couple general remarks first.
All right, thank you.
Okay, glad the audio is working. We'll test the slides in just a moment. So climate's a problem, obviously, because it's big. And therefore, we think that we need to get very large, scaled-up direct air capture facilities and fleets of facilities. And frankly, we think that we need to ignite a carbon removal industry where there are many players capturing CO2 back from the atmosphere, storing it underground, or using it to make environmentally beneficial products to help us tackle the challenge. So what do we need to do to get there? I'm going to offer a couple of ideas, and then I will show some slides and talk about a couple of use cases for the technology. So we think that we need to demonstrate that direct air capture is feasible, affordable, and available by building some actual large-scale commercial facilities, building on what Climeworks has done to get to bigger and bigger scales. We think that operating plants are really what convince policymakers and governments that any remaining doubts of the technology should be put away and that we should move forward. We also think that we, as an industry, need to tell a credible and simple and compelling story about how direct air capture and carbon removal can play a role in a very prosperous future that avoids the worst of climate change. And we think that by telling a simple story, connecting with the public, connecting with business leaders and decision makers, we can rally the support that the direct air capture field needs. So number 3, and this is very important, we need to advocate for a business and a policy environment that lets us scale. So I'll say more about this in a few moments, but in a lot of parts of the world, that the amount of revenue that you can earn for capturing and permanently storing atmospheric carbon is zero. The amount of government-backed or market-backed revenue is still zero in many parts of the world. So happily, we have some leading markets starting to change that. Happily, Climeworks and ourselves and the others in the field are starting to engage the public and to engage some corporate leaders who are starting to do more voluntarily, but we need big markets. So we need advancement on the policy front. So let me start up some slides here. And maybe just a quick, started at the end. Maybe just a quick check from someone in the room can give me a thumbs up if you can see that. Perfect, thank you. So those are my comments about the DAC field in general and where we need to go from here. So now I'd like to take a couple moments and talk a little bit about what we're doing at Carbon Engineering. So I think in the interest of time, what I'm going to do is skip to a couple of use cases. And this will probably be very well covered or very well known material to many people in the audience, but hopefully some repetition is helpful, and hopefully some of our perspectives on these use cases is helpful. So something that we've been working on, I know Climeworks and Global Thermostat have been working on as well, is about using CO2 captured from the atmosphere as a feedstock for products. The product that we're really excited about is fuels, more so than solid carbon products, because the transportation industry has about $3 trillion worth of liquid hydrocarbon fuels that it consumes every year. This year will of course be different, but $3 trillion is a lot of value. There's a lot of segments of the transportation sector that don't necessarily lend themselves to electrification with batteries or potentially even with fuel cells. And so the ability to capture atmospheric CO2, and whether it's through thermocatalytics or electrochemical reactions, combine that with renewable hydrogen that we can produce from clean electricity and make fuels, we think this is a major strategic addition to the energy system and to our strategy as we tackle global emissions from transportation. So this is a use case we've put a lot of effort into at Carbon Engineering. We've made Fischer-Tropsch fuels at our site in Squamish. There's an example of our fuels burning beside some conventional diesel in the image there. So these fuels are a lot better for air pollution as well as for the climate. And we find them, very exciting as a prospect to reduce emissions. The challenge right now is that a lot of existing carbon policy or a lot of existing fuel policy either doesn't contemplate fuels made from atmospheric CO2 or in some cases doesn't supply quite adequate revenue for these to make commercial sense. So I know that Climeworks and ourselves are working on some early projects and hopefully we'll get there. But this is one of these cases where we need more in the policy realm. Another use case that we're working on at Carbon Engineering is one involving enhanced oil recovery. We've put a lot of effort here. We're doing some initial projects down in Texas, but I also want to say a few technical things about this use case because I think quite often there's some negative response or sort of negative emotions about any solutions that involve oil and the production of oil. But the really important thing that we and our partners, Occidental Petroleum and 1.5, are doing with enhanced oil recovery is we're managing the flows of atmospheric carbon into the oil reservoir in accordance with the flows of the oil out, so that at a minimum, even our very first projects will inject as much carbon into the reservoir for permanent storage as what comes out and is then left in the atmosphere after the crude is refined and used in vehicle. So if we balance the carbon cycle around our project and don't go further, then what we end up with is carbon neutral crude or carbon neutral fuels, which from an energy systems perspective is somewhat analogous to the fuel synthesis case I just showed. And what's much more likely to happen is that our partners, Occidental, 1.5, and ourselves, will actually push this into a negative carbon balance, so that we can negate the environmental impacts of the crude, but that we can also do net carbon removal into oil reservoirs. And the reason we want to do this, the reason we think it's a helpful thing, is that there's a lot of very well characterized, well understood oil reservoirs out there. There's a lot of injection equipment and pipelines that are already built today, ironically, to inject fossil CO2 into oil reservoirs. So this actually gives us a lot of infrastructure and a lot of industry knowledge to build on as we start scaling up direct air capture and doing early facilities. So this is a rendering we just released of a project we're working on with those partners, slated for the Permian Basin in the United States. So we're about 25,000 man hours into engineering this facility. It will capture around 1 million tons of CO2 from the air each year. So that's equivalent to the emissions of 250,000 individual cars. It's also the carbon absorption that is done by about 40 million trees. And yet this facility will only sit on about 100 acres. So that's a lot of carbon work for fairly minimal land footprint. And this CO2 will be delivered to Occidental Petroleum for injection and permanent storage, which is mandated by the California Air Resources Board, which is the regulator of the government-mandated carbon credit program through which this facility will generate credits and earn revenue. So it's going to be very much a best-in-class direct air capture and permanent storage facility. So I think the last use case that I'd like to talk about is also actually the most important. So we call this DAC with permanent geological sequestration. We sometimes call it standalone carbon removal, to convey that no other product is being produced or no other source of emissions is coming from anywhere. And this is simply the configuration where DAC is used to sequester CO2 in permanent formations underground and to do nothing else. And those of us in the climate community and who have been working on carbon removal for a lot of years will be very familiar with this graph. It shows the many tens of billions of tons of emissions that are going to the atmosphere. And this is one analysis from Goldman Sachs, but there have been many over the years. It also shows the estimated cost for eliminating those emissions at source. So ourselves and the National Academies of Sciences and even the IPCC in their 1.5 degree report have all highlighted the need for a carbon removal solution to help us tackle this curve and to help control the costs of eliminating all of our emissions, and then to give us the option to go net negative and to actually remove more CO2 from the atmosphere than we are emitting to it in deep future years, if our current concentrations of CO2 prove too sensitive for the climate. So we think that direct air capture with permanent geological sequestration in a standalone mode is critically important to reducing the 40 billion tons of emissions we already have, to tackling the emissions that are soon to come, and to eventually going negative. So much like Climeworks and much like our other colleagues in this field, everything we're doing is in pursuit of reaching this goal of gigaton scale carbon removal into permanent storage underground and without land and water use impacts associated with some of the biological approaches. So to be clear, we think all the approaches are going to be needed, but we're definitely going to need some approaches like DAC that have very low land and water use and very high certainty of the CO2. So I'll end there, and I'm happy to take any questions. in whatever format the summit is taking place.
Jeff, this was your applause. I hope you could hear it.
I did. Thank you.
Jeff, thank you very much for joining. I think it's 6 a.m. now for you, huh?
That's right.
So early morning. And any questions from the audience before we go to the next speaker? Please.
Jeff, I'm questioning the case that you bring more carbon down into the ground with oil recovery than you bring carbon up with the oil. As far as I know, 1 liter of fuel will create something like 1,300 liters of carbon dioxide at atmospheric conditions. So it would be an awful lot of compression, or either you have some other tricks so that more carbon is staying in the ground than you will bring up.
Yeah, I mean, I think one comment, you used a volume metric. So the fuel is a liquid and the gas is obviously a gas. So the 1,000 liters to 1 liter is a volume metric, not a mass metric. So it's true that in conventional enhanced oil recovery, the way it's been done in previous decades, if you were to just replace the stream of CO2 that were going into those operations, those would not be carbon neutral or carbon negative. They'd be better, a lot better than conventional oil, but they'd still be carbon positive. So the trick is to understand the impact of the regulations that are happening in the United States, like California's low carbon fuel standard, and to understand the way that they do accounting and the way that they credit these projects that will put CO2 into those reservoirs, and then to look at where those financial incentives lead the operators. And when you have credits that are worth $200 per ton each, but are only issued on net atmospheric CO2 sequestered, then there's a very strong incentive to manage the individual reservoir into which you're doing your sequestration to enhance the economics of both the carbon removal as well as the production of oil. So it's not true that every EOR field or every operation in history would have been carbon neutral or carbon negative, but it is true that you can design projects to be carbon neutral and carbon negative, which is what ourselves and our partners are doing now.
All right. Thank you, Jeff. Please stay in the Zoom call because afterwards we will have the panel also with you. We now switch to the next speaker, to Niklas Eisenberger from Global Thermostat. Niklas, you're ready.
Good morning and good afternoon.
Good morning, good afternoon. Niklas is a pioneer in clean economy and long-time senior advisor to Global Thermostat, right? Niklas has worked for 2 decades to advance the clean technology industry. He is also founder and managing partner of Pure Energy Partners, a venture capitalist firm that invests in high-impact, high-potential, clean economy companies. Niklas, welcome. We can see you. Very good.
Thank you so much. And greetings from Connecticut, where we are not suffering from the wildfires that our colleagues in California are, but have recently had serious set of storms, hurricanes, even tornadoes. So it's very real to all of us. I wish I could be there with all of you today. I was very much looking forward to this important event. These are strange times for us all. I hope all of you are making this transition from summer to fall in your lives and your professions with the least amount of difficulty. I want to thank Climeworks for putting together this event and for hosting us. This is Christoph and Jan and your entire team. I know how much work you've put into this effort despite the adversity, and it's very much appreciated to be able to be here today, even if remotely. And I want to thank my colleague Jeff at Carbon Engineering and all the speakers for the efforts, as well as all of you. All of you have showed up in person today, calculating what kind of risks you're taking, shows your dedication to addressing this very important challenge, and all of you online. This is a major milestone in the development of the direct air capture industry, and I think we should be proud that we've gotten here. It's been a long journey, and there's a lot more work to do, but this is a very important moment, and I think we should make the most of it. So I'm Nicholas Eisenberger, a longtime investor and entrepreneur in the broader clean energy space, and a proud longtime senior advisor to the board of Global Thermostat. I want to tell you a little bit today to build on the comments of my colleagues about Global Thermostat and our perspective, some of GT's origins, its status, and where we're going to help contextualize this conversation for all of you and help accelerate our conversations and this journey for the entire industry. So I'm going to share my screen. Okay. I can see that you can see that. So let me tell you, a little bit to start about the origins of Global Thermostat to help put some context around the vision of the founders of this company, who I also bring you their greetings from Dr. Kjetil Wilhelmsen, Dr. Peter Eisenberger, who, yes, is my father, and our board chairman, Edgar Bronfman Jr. Dr. Kjetil Wilhelmsen and Dr. Eisenberger really came together first around 2006 at Columbia University, and really Dr. Kjetil Wilhelmsen brought this international perspective as the author of the carbon market mechanism and the Kyoto Protocol, and a career of dealing at an international level, trying to look at how you could use the tools of economics to drive solutions to climate change, and really came up with this perspective that we had this challenge in the air, and it was equally distributed, and that you could, in theory, enable all the nations of the earth to participate in the benefits of eliminating the challenges of climate change if you could find a way to extract carbon from the air. And my father, a material scientist, a physicist, and her partnered together to try to see if this idea was in fact feasible. So from the very first moment, this issue, the drive for Global Thermostat, as you heard from my peers in the industry, really has been a drive to address climate change at scale. And we were lucky enough to meet an investor early on in our journey who had the insight, the expertise, and the patience, and a shared passion in a positive impact to deploy his and his family's capital on something as important to this. And Edgar Bronfman Jr. has been an amazing chairman for our company, and we have been on this long journey together, which, as I think you've heard from Christoph and Jan and Jeff, we've now all been a decade or more going down this road. And at first it wasn't so easy, but as you've heard also, the last year or 18 months have been quite exciting, crazy at times. So we received our first investment in 2010 and very quickly demonstrated the technology at SRI and its technical viability. So what is the Global Thermostat technology, and how does it work? It's not too dissimilar at a macro level with Climeworks. It's a solid sorbent technology. You bring in air, you pass it over a large surface area honeycomb monolith coated with an amine, and it attracts CO2, and then you heat up that using low temperature heat, as I'll discuss, and you drive off the CO2 and you can collect it. Very, very simple concept at the macro level. Obviously the details matter significantly. One of the other things that Global Thermostat is able to do is capture CO2 from flue gas as well. And that, we believe, that flexibility has great virtues. There is, as you've heard, a tremendous amount of emissions, ongoing emissions that need to be mitigated in addition to taking it out from the air. And there are certain advantages in terms of temperature and contamination from doing so as well. And you get to optimize mixing air and flue gas for both cost and efficiency perspectives. So that's something that enables you to think about, essentially carbon negative power plants that are even gas powered where you can go to a source and extract more CO2, both from that source and from the air, than is being emitted at a very significant scale. Some of the key performance advantages or features of global thermostat, you really have this highly efficient contactor where you're really able to pass air through it and capture at an optimized level very quickly, and that allows for high capital utilization. You're also able to cycle the process very, very quickly. Again, enables you to maximize your capital utilization. And then, as I mentioned, we're able to utilize very, very low temperature heat, sub 95 degrees C, to be able to generate this process. So that is both, in certain circumstances, widely abundant and certainly less expensive than high temperature heat. We also have designed our Zorban apparatus essentially like a printer cartridge or the famous razor blade, so that the latest generations of the cartridge can be substituted and replaced as needed for our implementations. And that also brings about great efficiencies in terms of long-term cost. So like our colleagues, as you've heard, we believe we're on a cost trajectory, won't go into specific numbers, but that really sees us getting down to a place where this is extremely, extremely viable from a societal and business perspective to both address climate change and start to generate economic returns that are very attractive. And I want to just linger on this for one moment, because the cost discussion since essentially the beginning of this industry in 2010, 2011, has been an inhibiting factor for, I think, action to date. There has been this perception that costs are inevitably high, and we feel very confident in our technology that we can get to factors that are as low or lower than you've heard some of the discussion today, and in all cases viable for a cost for society to bear to address climate change, and viable for generating a very attractive profit. So I look forward to the day. I think we're getting close when the issue of cost is removed from the table as an objection for action around direct air capture and for societal mobilization around direct air capture. Of course, we need to demonstrate all this to the public and to policymakers, but I think collectively as an industry, we're well on our way to doing that. Over the years, we have demonstrated improvements, as you heard Jan and Christoph talk about, the stepwise improvement in the technology. We are on a very similar trajectory from our first pilot in 2011 to the carburetor demo in 2013 to a containerized unit in Huntsville, Alabama last year, where significant improvements both in total capacity, in velocity in capital utilization, velocity of air, and in mechanics and overall capture efficiency. One thing I just want to say, we've touched on it already in some of the discussions, but we really believe that there are very significant, very attractive opportunities to both do carbon removal and generate economic returns by substituting the fossil-based economy we have over time to an air-based carbon economy, where humanity uses a tremendous amount of carbon. It's all around us in our fuels and fertilizers and chemicals and plastics and building materials. And these are both today and potentially in the future, as population grows, as economic activity grows, there is enough sources of durable carbon, building materials and other things of that nature, substituting carbon fibers for steel, using CO2 in both cements and aggregates, which we use at a multi-billion dollar ton per year basis. There is an opportunity to do a lot of the carbon removal work that we need to do over time in the form of substituting fossil carbon for air carbon. So we're very excited about that, and that has been our primary focus. And we continue to believe that that is something where you can have a win-win for society, a positive vision that you can bring forward to society, where you can use this resource in the air, which is causing us a problem, capture it, convert it into a material that societies around the world need for their development, and also do so on a more equitable basis. We think that together as an industry, we need to bring that positive vision more to the center so people see we're not just averting a disaster, we're not just treating a pandemic or crisis, but we're actually building a better future. Of course, sequestration will probably also need to be a part of the equation, and we do see growing demand for that. A lot of the corporates coming online are now focused on sequestration. We're very excited about that as well and collaborating with many of them to pursue those opportunities, and we'll continue to do so. Global Thermostat today is pursuing a broad spectrum of commercial opportunities. You may have heard of the Joint Defense Agreement, Joint Development Agreement, excuse me. We have signed last year with ExxonMobil. We're very excited about that. Been working hand in hand with them, really focused on how do we scale this technology for global climate change and make it at the scale that global industry will find both interesting and economically viable. So stay tuned on that front. We've continued to work with Exxon, and that partnership has been very fruitful on both sides. And hopefully you'll be hearing more news on that soon. We see we have a number of other agreements in place and in process with Saudi Aramco and Aqua Power in the Middle East. For pilot projects, we're talking to very significant players in the power sector for decarbonizing the power sector, and have agreements with some of the large industrial gas companies on a strategic basis to think about supplying CO2 from air to their customers, and are looking at projects at a very significant scale on the material and fuel front with some of the world's largest infrastructure companies. So on an economic basis, as my colleagues in the industry have stated, as they're experiencing themselves, the interest has significantly ramped up in just the last year, 18 months, and we're being very careful to identify which opportunities make the most sense in terms of scaling the technology and scaling the business. However, I want to really emphasize that as a company, the founders and the team are really laser focused on how do we address climate at scale. That is the task here. That is the urgent existential issue. And that is where we're orienting the entire company to do our best to contribute to success. So we have a number of different dimensions in which we're doing that. We have significant efforts internally in terms of building on our significant patent foundation to think about how can we make this solution more ready, more at scale, more cost effective. And we've recently filed 2 exciting patents, which we think have significant potential for scaling. One is the Direct Air Capture Plus, which basically enables us to use one embodiment for both flue gas and direct air capture. And that opens up all kinds of possibilities for, as I mentioned, carbon negative power plants, potentially even making renewable energy dispatchable. And also a continuous motion system, where obviously you can get certain benefits of a continuous motion versus a batch system. We've opened a new technology center in Denver, and have a full suite of activities there that are, as I said, focused on how do we scale this for addressing climate change. We're also very pleased that the US government, among others, has really started to ramp up its interest in this space, and we have partnered, we're increasing our partnerships with the DOE. We've received over 5 DOE awards in the last few years, including one last week, to demonstrate the continuous motion process. And overall, as it says here, we're really focused on these issues that we see down the road will be necessary to really run as fast as we can as a company and as an industry to scale. So I mentioned our joint development agreement with Exxon. We are building on that with key industrial partners around the world. we really view our goal to provide the technology that can cost effectively and scalably address this, but we know that there are organizations already that have the engineering expertise, have the development expertise, the geophysical expertise, the product expertise that we will never gain. So our strategy is to really identify the leaders in each of these areas, monolith and absorbent and supply chain, manufacturing, the end users and the different applications, and partner with them to find ways to scale this up, test it, develop it, scale it, and go forward. So that is our core focus, and we invite others in the industry across the world to join us in that, that journey. We have a number of new plants that we're building on that trajectory that are under construction today that are really intended to be demo plants for scaling up at a multi-million ton per year capacity. And I also just want to end by saying here that we believe that we're excited about our company, we're excited about our trajectory, but we also know that the task here is so huge that this is something that we need a very successful industry. And it's been a pleasure over the last decade to collaborate with Jan and Christoph and Jeff and his colleagues. And we have started to ramp up that collaboration because we see that the opportunity is so huge here and the need to rise the tide for all boats is so urgent. And just in July, we hosted at the Elk Coast Institute for Mindful and Sustainable Innovation, we hosted a DAC Mobilization Summit. All of our peers in the industry participated, and we had over 70 participants spending several weeks in developing working papers, which we're going to issue a report soon about how can we scale up direct air capture as quickly as possible, and what role can policymakers and finance, commercial partners, civil society play in helping us to do that. So notionally, we have an agreement across some of the leading players, all of us, to try to build on that informal collaboration and see how we can better engage with our various stakeholders, educate, engage, listen, advocate for the growth of this industry. So I hope you'll stay tuned and more from that. I'm going to be spending, and Global Thermostat has allocated some of my time to really invest in that collaboration. And I think that hopefully says to all of you how dedicated we all are in this industry to try to address this challenge. So today is another example of that, and the spirit of collaboration and inviting us all in to speak here is a wonderful expression of that. So stay tuned for more, and thank you very much.
Niklas, please, thank you so much. Please stay in the Zoom. You just mentioned we want to scale up, and we also want to scale up the industry, right? The negative emission industry, the direct air capture industry. So, and that's exactly my point now. Before we go to the coffee break, and you were listening so curious, and you really deserved a coffee break, and you get also your question, just getting the 3 leading direct air capture companies on stage with Climeworks, with Global Thermostat, and with Carbon Engineering. So please, Jan and Christoph, one more time, join me on stage and have a discussion about how, if you talk about scale up, Jeff, Niklas, Jan, Christoph, how will the direct air capture industry look like in 2050? You together. And you are the 3 leading companies, or did we miss any relevant players here?
We're indeed missing companies.
Yeah.
So there are a handful of companies, yes.
Okay. Good. How do you see the direct air capture industry? Because that's very interesting for us as companies, as investors, as journalists. How do you see the industry in, let's say, 20 to 30 years in 2050?
Well, maybe to start, first of all, I think the concept of developing an industry is a very, very important one. And just to note that, I was, when talking to customers, but also to states, I always heard from many people, hey, if I'm considering basing my strategy on what you are doing, it is important that there is at least a handful of companies that is doing that. Otherwise, it's just like too much of risk for myself. So from that point of view, I think, and I believe that's valid for all of us, and curious to hear your comments from remotely. I think it's really important that there is currently a small group, and I believe there will be an even larger group looking at what is happening in the field currently in 2050. I would not be too surprised to have something like, well, at least a double-digit number of serious players in this field, which we are currently leading. And I believe that's what this world needs and also what the market needs to develop.
So we need more players, we need to grow the industry, we need to become like a really renowned industry. Do you already have an association, Niklas?
So we're trying to put that together today. As that's what I was saying, stay tuned. We do have, we've come together and said this is so important, we need to collaborate, and we've identified a couple of areas, as I mentioned, in terms of market education, engagement, policy, where we think we can immediately start, and in fact have immediately started to collaborate. And we're looking at opportunities to formalize that. To just quickly address that question, I guess I would say a couple things. One is, yes, I agree that we should always bet on human ingenuity, that there are more solutions out there, and I anticipate, and there are companies that aren't present here today. We welcome them to join us in this journey. And human ingenuity is a great thing, and so we should nurture that. That said, I do think that there is still this instinctual reaction I see as I'm out there talking to leaders to say, oh, we need R&D. Okay, direct air capture is important. Let's invest in R&D and find new solutions. Yes, as I said, we should always put some of our resource to work for more ingenuity. But you do have a set of players here where they are really essentially ready for scaling, and we need to make sure we start down that road quickly. And so we do need that support to really get the technologies that we have at play to that next level, in addition to investing in new solutions. I guess the final thing I'll just quickly say is that this task is so urgent that we at Global Thermostat are open to sharing, to cross-licensing, to other types of solutions that, if it's necessary, if we must collaborate globally as a species to address this climate crisis, maybe there are combinations of our different solutions that in different contexts around the world will work best. And so we're open to that conversation as time goes on.
Thank you, Niklas. Thank you, Niklas. There's also one more question from the audience. Jeff, I see you're still with us. Please, your question.
Yes, thank you very much. My name is Axel Michaelova from Perspectives Climate Change, and my question would be to all the three of you: what are the policy instruments that you would like to see from national and governments and international regimes to drive up this upscaling that you are all looking for?
Yeah.
Yeah, I'd love to comment on that for just a moment. I think in terms of policy instruments, there's a couple ways to skin this cat, but fundamentally what Climeworks and Global Thermostat and ourselves need to deploy facilities and to deploy projects is revenue certainty. I mean, it sounds simple, but we always have to remind ourselves that water flows downhill and finance flows to profitable projects. So we need revenue certainty that we can bring in equity and debt to help us build large projects. So in North America, there's a little bit of a renaissance in carbon capture happening right now, and air capture is getting swept up in that. And that's happening because we have credit deficit-based programs that measure life cycle carbon reductions growing in several states like California, Oregon, Washington, a couple of our provinces in Canada, and soon to be national in Canada. And those are combining with tax credit mechanisms that have been implemented federally in the United States. So it's actually the credit deficit program plus the tax credit that is proving to be the critical mass of revenue certainty that's starting to really draw investors into carbon capture and air capture. I think you could do this a number of different ways in terms of policy instruments. I think you could do contract for differences. You could do direct government procurement for carbon removal services from projects that provide it. You could do tax-exempt bonds or tax-exempt financing methods. I think there's legal and regulatory precedent in different parts of the world and different countries that might make country X, Y, or Z choose one solution over another. But fundamentally, we need to make revenue certainty available to these projects. If that sounds frightening from a cost perspective, we can start small and then start to scale the market or scale the policy bigger. But give the 3 companies here and the others who are soon to join us sort of a policy environment to get started within. I think that's the key to success.
Thank you, Jeff. Anything to add?
Yeah, maybe as I typically like to look into the past to extrapolate for the future. And actually, we do have one data point, and that is the Californian Low Carbon Fuel Standard, which was mentioned by Director Uduak and by Roger Aines before. And Jeff, if I may say that, please correct me if I depict it wrong. But what the Low Carbon Fuel Standard did is it created a huge equity investment round on the side of carbon engineering, right? You announced the great 70 million round last year, and that really goes back to, or that's my interpretation, back to this market mechanism. Our investors looked at carbon engineering and said, oh wow, they're doing a 70 million round. We have to do the same or even more. And in such, of course, I'm oversimplifying, but that might help us to condense or to find the problem to be solved. The Californian Low Carbon Fuel Standard has been quite effective already in stimulating the direct air capture industry. And if there were more of such mechanisms, clearly it would catalyze more.
I hope this answered your question.
Maybe one very quick addition, speaking to anyone who is currently designing policies, I think what is important, and it's just underlying what Jeff just said before, any policies should follow the industry's planned scale-up curves in both in costs and volume. So we don't need a policy giving $500 per ton through some instrument at a $10 million per year scale. So that's not needed. We might need that cost range for a small volume or for the first couple of million tons, and then it can decrease. But it is really important to not just see the end game. 30 years down the road, billions of tons taxed with some CO2 tax at a low cost level, but we need a policy that paves the way over the next decade or decades.
Any more questions from the audience, or shall we go to the coffee break, to the wonderful weather outside? Last question? No? We go to the coffee break, right? Jeff, Niklas, thank you so much. We are doing coffee break now. You're doing breakfast, right?
Exactly. Thank you very much for having us.
Thanks, Jeff and Niklas.
Thank you.
Thank you very much.
Thank you.
Thanks for joining. So half an hour coffee break. Enjoy. You can use the terrace outside. Never forget the rules, but you already know. I don't have to repeat. 1.5 meter, no kissing, no hugging. So, ladies and gentlemen, welcome back from the break. I hope you enjoyed the coffee break. Also, welcome back to the online participants. Now we really have a super important topic. I want to say that one of the most important topics and subjects of today. It's about the overall life cycle assessment of the direct air capture technology. So what if you calculate all energy used, all transportation, all recycling and put it all to a balanced scorecard and really assess if the benefits outperform the impact, because we need a lot of energy, we need a lot of heat, we need a lot of transportation, we need a lot of recycling in the end. So he's currently doing research on this relevant topic. So please welcome with me Professor André Bardow on stage from ETH Zurich. Professor Bardow is also a fellow of the Royal Chemical Society and chairs the technical committee for thermodynamics at VDE, the Association of German Engineers. But now you live in Zurich, and we are very happy to have you here on stage. Professor Bardow, please.
Thank you very much. Okay, I think that's a privilege of the local speaker to get an applause when you come on stage, and I also am excited to be here. It's also my first public talk since February. So I'm really thankful for you making the effort, for Climeworks organizing this event, for shifting the organization, and for all the people who made this possible. And for you to join on this beautiful day to listen about the life cycle assessment of direct air capture, which I'm going to be talking about. The program has not been honest, but my first slide is honest because the work I'm going to be presenting has actually not been done by me, but by a smart PhD student, and her name is Sarah Deutz. And hopefully she's watching online, and then she goes back to finishing her PhD thesis. Okay, now I'm going to be talking life cycle assessment, and as Niels mentioned, so I'm going to be looking at the environmental impact of direct air capture. I'm going to asking, does this from an environmental viewpoint make sense? And for a lot of people, this might be a really dumb question to ask. Why? Now, obviously, direct air capture is the great thing in mitigating climate change. I think, as I put it in the picture, you could say that Christoph and Jan and the other companies, they climbed the steepest mountain that there is in mitigating climate change. They are the heroes. They managed to do the important thing. They are sucking CO2 out of the atmosphere. So obviously, these guys are great for the environment. But this picture is incomplete. And actually, to be quite honest, this is not even a mountain, but this is actually an iceberg. And as we know in life cycle assessment, there's great that these guys suck up CO2 from the air, but there's something hidden underground, and that's the work they have been doing to be able to do so. And we call it the life cycle of the direct air capture technology, which means you have to build the plant from materials which are extracted from the environment. We build the plant, the adsorbents, the foundations. We have transport, the energy use. You have the end of life where you hopefully recycle some of the materials. But in the end, you will also deposit some materials to the environment. And all of these activities generate CO2 on their own. And in particular, as mentioned, the energy demand is also usually related to CO2 emissions. So one question I want to answer in this talk is, does direct air capture in fact reduce CO2 but over the full life cycle? Because that is the key question we should answer, and only then it will be really a negative emissions technology. And the second question is that yes, we in the room are all convinced that CO2 is the greatest problem in the world. Maybe Corona told us there are other problems to the world, and also environmentally there are other issues around. And we should be aware, and I think in particular if our target is to transition in the economy so far to a low carbon, to a negative societies, then other environmental impacts might increase. So we need to make sure that we're not only reducing carbon and kill all the fish at the same time. So that's why we need to look out for other environmental impacts. And that's the other second question I want to be answering. That is, how much does direct air capture increase other environmental impacts? Because one thing is a given. If we start deploying a technology like direct air capture, we will harm the environment. The question is just how much and what are the trade-offs. Okay. So what we did, we looked at life cycle assessment for a specific technology, and here I'm thankful for Climeworks because they shared data for us from their direct air capture plants in Switzerland and Iceland with us, and we looked what are the environmental impacts from capturing 1 kilogram of CO2 from the plant. I should mention that they provided data, but they didn't pay me, because this was a public paid project, so I was only, my duties were due to the taxpayer of Germany. Okay, so we collected all the data on the plant construction, on the environment surveillance, on the recycling, and then we did the balances, and there was a lot of work, but I take the shortcut for the short presentation and just show you the result. So what is the carbon footprint for the Climeworks plants in Iceland and in Switzerland? Now, as I said, they are up the mountain, they are sucking CO2 out of the air, so that's a -1 carbon footprint, the negative carbon footprint that you would get from just sucking up by miracle. But they have to put in some effort, and this is the trade-off you are seeing, and that's the numbers where you end up ultimately for the carbon footprint of the capture technology. So the good news is, or the bad news is, it's not the -1, but the good news and the important one, it's minus. And it's more than 90%, it's more than 80% for Switzerland. So we conclude direct air capture has a minus sign, it does indeed reduce CO2 emissions. And we can look where are the remaining CO2 emissions coming from. And these colors might not be easy to see, but you see that the highest contribution is due to the energy supply we have been discussing. Even in Switzerland, where they are employing waste heat, still the largest contribution is from the electricity that is used. But you should also notice, if you go to low-carbon locations like Iceland, then the adsorbent becomes relevant and also the plant construction. So the adsorbent makes up to 34% of the carbon footprint that remains. But as we've seen, the key requisite, and it was mentioned before, is clean electricity. So that's why I show you this complicated graph, and I apologize, but I hope it's worthwhile. So what are you seeing here? You're seeing again the carbon footprint plotted on the y-axis, goes down to -1, and I plotted it over the carbon footprint of the electricity we employ. And here you can pick your favorite location on the globe and say which kind of electricity do you want to employ and what will be the carbon footprint of the CO2 that you capture. And what you see is there's a zero line, and not all countries provide electricity that is sufficient to supply a DAC plant so that we get to negative emissions. In particular, and I say this with a broken heart, my home country of Germany, and the impacts are larger because they are life cycle, than you might know, than life cycle emissions. So this is for a heat pump, where we use a heat pump, we can use waste heat, then this gets a lot better, obviously. And now you also see that these guys cleverly pick the locations where they put the plants. One, the plant that is using waste heat, and the other plant in Iceland, in particular this geothermal power plant, where we have detailed data, really provides very, very clean electricity. But as you clearly see, the energy supply is the key to the technology. So what we have been asked, what's the plan for the future? And here you see future projections for improvement, in particular in energy efficiency. And you see this could be have an enormous impact. It might not seem much, but if you see how much you move on the y-axis, so that more dirtier power would take you still to carbon negative, so this is really worthwhile. Okay, so the good news is direct capture reduces CO2. The bad news is, if you're from Germany, not everywhere today, you need sufficient low energy supply. Okay, so we saw direct air capture reduces CO2, but I didn't tell you the full story because I said it should be over the full life cycle. And what I've shown you up to now is Jan and Christoph sucking up CO2 out of the air and then maybe releasing it again, which would be a waste of time and just bad for the environment. So the question is, what's next? So and we've discussed a lot of possible markets. And we looked, I will show you two small examples on possible markets, and one is to do CO2 utilization, where it takes the CO2 as a carbon feedstock and convert it into methane in this example, and the other one is to put it underground. And this takes us then to the full life cycle of the CO2, captured CO2. So how does the graph look like? I jumped right to the results for carbon dioxide removal. That is, we take the CO2, pump it, compress it, transport it, and store it underground. And this is a full graph. It's the same picture, and I only moved the axis a little bit, so it looks very, very similar. So the conclusions are very, very similar. And the important line is now here, the zero line. And you see that in many countries with a sufficient low carbon footprint, direct air capture could be carbon negative, could be a carbon negative technology. So that's great. So Again, not everywhere, but negative emissions are possible, and they are possible today, which I find important, because it sounds like the big dream for the future. No, you can do this in the right places today. So what about converting it to methane, the CO2 to methane? This, you end up with this line. Now the benchmark is also shown here, is now fossil-based methane. And what do you see is that we need much, much cleaner electricity in order to just reduce CO2 emissions compared to fossil-based methane. So you will do this only with very, very clean electricity. And then, and this should be obvious, we will never get to carbon negative, but in the best case, we will cycle the CO2 so we could get to carbon neutral fuels and chemicals. So it can reduce, but the electricity has to be very low carbon electricity, but it's important to go to carbon feedstocks. Okay, so I answered the first question, and I will be very brief on the second question. So what are the trade-offs and other environmental impacts? And I just show you this slide where we looked at the company webpage where you had the goal to capture 1% of the CO2, global CO2 emissions. So we asked how many percents will you be increasing the impacts in our other dimensions? And the good news is that this axis ends with 0.1%. So that means for us that these are very different. So this is toxicity and eutrophication and so forth. So it's difficult to account this. But what we to balance them against each other. But what you see is that based on the data we've seen, that the other impacts do increase, but they do not increase excessively. So we see no big trade-offs that we run into other big environmental problems as a downside. So with this brief overview, I'm already done with my time. So I hope I could convince you that we need to look for the iceberg, that we need to look at the full life cycle. That direct air capture technology is already feasible to reduce in the right places atmospheric CO2, can even lead to negative emissions, or can be with sufficient clean electricity go to carbon neutral fuels and chemicals. Low carbon energy is a key supply, which we didn't discuss much, and the adsorbent and plants become important. Once we are in this low carbon world, then we really need to look for other things. And with this, and we've not seen excessive impacts in other dimensions. So with this, I thank you for your attention and the funding agency, and I'm happy to take questions.
So André, I'm right, this was the most important discussion of today. And now I know why you like Iceland, working there, because of so much green energy. Yeah? And how do you see the efficiency of carbon dioxide and direct air capture in 2030?
So I think it's these bars, I think they sometimes hide it. They look, okay, the lines go down and the slope changes a little bit, but it's really, it's enormous change also in environmental impacts if you go into this. So I think we have to become more efficient. And I'm with, I think, Roger's talk. It's great that you use waste heat, but I would not believe in an industry of the size we are planning for that will run on free green energy everywhere.
Yeah.
So I think energy efficiency is a key, and I think it's cost-wise, but it's also environmental impact-wise.
So we need something like fusion power.
Okay, I will not enter that debate, but my short answer is no. I think there's plenty, like Iceland is a location, and I think clean energy is for most of the things we are discussing is a prerequisite. So these things will not fly without sufficiently clean electricity, and we will not discuss a carbon neutral world without clean energy supply.
We were both worried about the Germans. Huh?
Yeah.
So any questions from the audience, please?
Professor Bardow, I have a little problem understanding what you said. Direct air capture is carbon positive and negative at some locations. Shouldn't you say carbon capture, direct air capture from Climeworks? This only related to your study with Climeworks.
Yes.
It doesn't say a bloody shit what other technologies do. Sorry.
Yeah, I said this on slide 3, and you picked it up. I'm sorry that due to time constraints, I didn't say this only applies on every slide, but thank you for this comment. I don't know whether you had to use the word shit, but this is probably a matter of parental background.
Any recommendations from your side, or?
I can only say maybe that I didn't want to show other data where I didn't have first-hand data. I can say I know the studies relating to carbon engineering technology, and the results are quite similar, in fact.
Please, yeah. No problem.
I was a little bit angry because it was just presented in the way, sorry. I think it's important that you look at all technologies that are around, and there are many around, and it would be good, and I would help you in a study to get access to other things.
Okay,
and if you have the proper title, then I would be happy too.
Yeah.
Thank you.
Thank you.
I would be most delighted, and believe me, I tried, and now I know the person who will enable me to. That's exciting.
We have some more questions.
Yeah, there was an article in one of the Nature journal Family recently about the environmental problems of ducks and stating a lot of water consumption. Could you comment on that article and whether this applies to all the technologies that were discussed today or whether it's an outlier?
I think I know the article. I have to admit I could not find the data sources they were using. I can speculate what they are doing. And I think I showed, so particularly the water demand that was to solvent-based, so where you use water technologies, and I believe they were using data, older data for the carbon engineering technology. This adsorption-based technologies are very, very, very different in water use, and so from our analysis, one of the 18 plots I showed you was water, and water was one of the smaller ones, and it's rather the issue whether you could generate water by these technologies than you consume water. So I think this. I will not quote the word, but this study was also limited, and the claims were maybe I followed their approach by making a too broad title about the data that was actually shown.
Thank you, André, for your explanations. Very helpful. I would have one question concerning the construction part you showed. So I would suppose that construction is not just the one event construction, but construction of all the different parts which go into the machine. Yeah. Okay.
Yes. Yeah. It's all the parts that go into the machine and the foundation and the stuff. I think that we've seen now being piled into the ground in Iceland. And I have to be, I apologize, I think there's a preprint available for all the data. The data I showed includes recycling, in particular of the metals and so forth. And this roughly halves the carbon footprint from the plant construction, if you assume. But I think for large-scale plants like this, you would assume that you recycle. But this I didn't mention.
Just a follow-up to the question before around the LCA of other technologies. So given solvent-based or all these different technologies, I think especially the distinction between carbon engineering and Climeworks approach, including water consumption, other environmental impacts, do you think science is already far enough to say whether there is a clear winner or one that would be better than the other when thinking about scaling this up?
I would say no, unfortunately not. So I'm happy. I think it's good that the companies come together, and I would be happy if they could share data, and this is all in a flux. So if you look at the paper, actually we didn't look at one adsorbent because there is not the adsorbent we will employ at scale. We literally try to look at the whole range and saying, are there some materials out there where people should stay away from an environmental perspective? So in that sense, I presented the data maybe more firm as they are. The error bars are enormous, and we really, I think what was important to me also to plot the range of impacts on the carbon footprint. I've showed it, but also on the other dimensions. So this is still a moving target, and I will not bet money on a winner, also from environmental viewpoint view. I think there's a fundamental differences, that is the water. That is just inherent to the systems. But yeah, because it's very different, but I think it has also not been fully mapped out yet.
Lisbacher, thank you very much for your very easily understandable presentation, because it's a very complicated thing to calculate these things, right? I think it's very important to really look at the input parameters for all the life cycle studies, because depending on those, the results can vary quite a bit. One important parameter I'm interested to know is the lifetime, the life expectancy of a system. And I think perhaps Climeworks has quite a bit of experience now, but when they have to replace the things, that's a very important parameter for the result. So what is the life expectancy you were calculating with?
Okay, that's true and really not true in a sense. As you've seen, the most important bit is the energy you are employing, huh? So at least for the carbon footprint. And for the plant life, you got me. I think it was 15 years or something like that for the plant construction. And basically, it's quite easy. You can scale the small bar, the 8%. That's 8 grams per kilogram of CO2. If you halve the lifetime or you double the lifetime, basically this would change. For the adsorbent, we had a cumulative data. Basically, we got a number. What is the amount of adsorbent used per kilogram of CO2 captured? And I think that was for today 8 grams, and hope to improve in the future. And that is basically, that's a cumulative number. So you could say, okay, I could, because it depends still on, it's still a moving target on so many parameters, but that's the number we used. And it scales all the impacts you have seen that are related to plant construction and to the adsorbent, which at the moment are not the most critical ones, but we need to keep an eye on them.
Okay, last question. Sorry, we have first on this side.
Yeah, this is Roland Dittmeier from KIT Karlsruhe. Thank you very much for the talk. I like LCA, and I mean the main conclusion you get also from your presentation is that it does make sense, of course, in the future world. So when everything is circular, renewable. However, we have to get there, and that has already also been said. So we should not look for the best possible solution. We should look for practical solutions that we can start to implement now. And that's why I hope that in the future, Germany will move to the left side and we get rid of the coal-based electricity production. So we should keep that in mind, that this is for now, and the LCA is with the data for the present system and not for the future system.
No. Actually, there were lines in for the future, but there were too many lines. I do agree, and I think it was an important statement also to be made. This should not, in my view, and I think even the companies share it, this should not be the one technology to save the climate. We need to reduce, we need the efficiency, we need all these elements. But I think I like studying this because to me this is really setting the upper bound. If our sole goal of our societies is to reduce CO2 emissions, that's the technology we could employ. And everything that is more expensive, you have to argue why you don't want to employ it. So if we get this upper bound down, it puts a pressure on all technologies. So I think it's important to study, but it will not be a miracle, and it needs to be part of the whole system solution.
All right. Thank you, André. We see it on the controversial discussion. It's very insightful and fruitful study you're doing. Thank you for your great work.
Thank you very much for your attention.
So he's already waiting in the line remotely for us. Keith Whiriskey, the Deputy Director of Bellona Europe. Bellona Foundation, if you might not know, is a non-profit, independent organization that aims to meet the fight in climate change. And so, Keith, can you hear us?
Good day.
Good day. Where are you?
I'm currently calling in from Brussels, so I need to apologize. I hear a lot of beeping. This tends to be the normal here.
Okay, we can see you and we can hear you very well. So, yeah, let's start the show. We are listening to you.
Awesome, perfect. Will my presentation be showed, or
you can share it in the Zoom?
Oh, okay. Apologies.
Yep.
Okay, cool.
Perfect.
All right, thank you for having me. I'll try to keep this presentation short and sweet.
But now we don't see you anymore. Maybe you can do it in the Zoom, or the tech team can help. Yeah, much better. Thank you.
Ace, thank you. So I'm going to give a short presentation on the interlinking of mitigation and carbon dioxide removal. And I'm going to focus on carbon capture and storage, and of course DAC, because there is the subject of the day. To give you the shortest introduction to Bologna, I would say that Bologna is an environmental NGO. It's originally founded in Oslo, but we have offices now in Brussels as well. And we try to take technologies from the lab and deploy them on industrial scale, get them scaled up so they can affect climate change in a real way in our lifetimes. And carbon dioxide removal and carbon negative has been a part of our story for 15 years now. If there's only two things you take away from this presentation, and I think it's been repeated many times already today, is that carbon dioxide removal is only supplementary to mitigation. It cannot replace it, and it should not be thought of replacing it. The way we think about this internally is that not making a mess in the first place is generally much easier than cleaning it up after you've made it. And then another one, and this might be quite surprising to some of you, but the more and more that carbon dioxide removal enters in the political conversation and the conversations here in Brussels, we see that there is a tendency for confusion between carbon dioxide mitigation and carbon dioxide removal. And I think keeping those very, very distinct is important for all the work we're trying to do. So reversing climate change is distinct from not making the climate worse. So carbon dioxide removal is distinct from normal mitigation and preventing CO2 concentrations in the atmosphere from increasing. Okay, with both of those, I believe many of you might have already seen a graph like this. Sometimes this makes me a little bit depressed. This graph here shows the cumulative CO2 emissions, annual CO2 emissions that we've had since 1980. So I was born around about here in 1985. So emissions have gone up constantly since I've been alive. We can see here that we've had departure points that would have given us a smoother ride down to a 1.5 degree world. So if we had taken climate change seriously in the early 2000s, it would have been a nice little slope. We could have reduced emissions annually at a small level. But as you can see, emissions have continued to go up, and we've failed to take really kind of stringent action on climate change. And this means that we get to this point where the task for us to reduce emissions now is becoming almost critical. The line here you can see is becoming almost vertical. That means the annual year-on-year reductions would have to be almost impossible. What this teaches us is that we should have tackled climate change sooner, but the moment that we can start reducing emissions in a really significant way, the better. The moment we can stop increasing CO2 atmospheric concentrations, the better. And this means we need to use as many technologies as possible to really start reducing CO2 emissions. But also, since this line gets so steep, and since our trajectory is so disastrous at this point, carbon dioxide removal comes in to play a supporting role to either buy some time or to get some leeway in how steep this decarbonization curve is. So at once it's a moment of desperation, but we have new technologies coming in line that allow us to continue having a conversation about how we do not let runaway climate change happen. So focusing on decarbonization and mitigation of our current emissions and our current stock of facilities, and we're very common talking about climate mitigation, carbon reduction from renewable energy. It's fantastic in that it doesn't produce CO2 emissions by itself. We have new energy carriers such as hydrogen and ammonia coming on that allow to make renewable energy more flexible. And we have new processes and product changes. So instead of producing products from plastic, we can produce them from something else, or we can maybe not use that product at all. These are all ways of preventing CO2 from being produced and preventing CO2 from entering the atmosphere. But I also want to reduce here CO2 transport and storage, CO2 capture, transport and storage, and how that can be used to significantly reduce emissions now and prevent increasing atmospheric concentrations of CO2. So we have products such as cement. So cement is produced from limestone. That chemical reaction releases CO2. So it would be possible to capture that CO2 and permanently store it. That means we can make cement in a way that would not harm the climate, or not significantly harm the climate. Similar is true for steel when produced with coking coal and gas. For waste, end-of-life waste products, instead of throwing that CO2 from incineration into the atmosphere, it could be permanently stored. So the end-of-life use of waste could also be near zero carbon. And another thing to add for CCS is that it comes at this megaton scale. It's a very chunky technology. And that means if you apply it, you're generally reducing emissions by 1 million tons or more is quite normal. So it's quite on a different scale from where air capture currently is in our conversations. But CCS does link to air capture in that they both share the CO2 transport and storage element. The last presentation made the point that unless we're permanently storing the CO2 that we're removing from the atmosphere, it won't be carbon dioxide removal. It won't be carbon negative. So deploying CCS and getting the network in place that enables industries to decarbonize, enables mitigation to happen. It means that in the future, we'll be able to add air capture into that system. So it means that the availability of DAC in the future can move a CO2 transport and storage network into, from a carbon mitigation network into a carbon dioxide removal network. So as we're mitigating today, that same network can use to reverse climate change in the future and put us into carbon negative territory. So this is to say that these technologies are not in competition with each other, they're synergetic in a system, and that the same infrastructure we use for significantly reducing emissions today can also be used for reversing climate change in the near future. Sorry to be a bit Eurocentric here, but I have an example of a future CO2 transport and storage grid in Europe. This is based on current proposed or future proposed projects, such as around Netherlands and Norway. Again, the access to transport and storage is critical if carbon dioxide removal is going to be negative. If we're capturing CO2 from the atmosphere, it has to be permanently removed and stored. And to labor the point on this a little bit, we've been trying to promote a simple way for people to assess a project to see if that project is actually carbon dioxide removal, if it will be providing carbon negative results. So here's a definition taken from a Tanzer and Ramirez from 2019, and it's 2 simple points. Does the carbon dioxide, is it physically removed from the atmosphere? Is the carbon that we're working with, is it geological form or is it atmospheric in form? And the second one, is a carbon dioxide permanently stored away from the atmosphere? So on the bottom left here, we can see that we have a normal business as usual. Imagine this being a normal cement plant that produces today and dumps its CO2 in the atmosphere. That's carbon additive, that's an emission, that's making climate change worse. In the center, we have a CCS plant. So again, applying CCS to the same cement plant. That's not a carbon negative plant, but it has the ability to go near carbon neutral. This is mitigation. It could be a 90% reduction over what would otherwise happen. So that's a significant improvement. We're no longer making climate change worse. But then with direct air capture in the same system, we can actually start removing CO2 from the atmosphere. And that means we're actually doing a drawdown. So the last example here would be very similar to the Climeworks facility in Iceland. So I'm just putting the slide up here to show that mitigation, so CCS applied to a fossil fuel plant or an industry plant, can reduce emissions, but it is not capturing and removing CO2 from the atmosphere. It's just preventing climate change from getting worse. While air capture and direct air capture with permanent storage and CCS allows us to remove CO2 from the atmosphere. These are providing different services, and they shouldn't be confused in policy or in accounting. I'll wait for your questions now when we get into the discussion. Thank you.
Thank you, Keith. It was an excellent overview, and you also shown to us the urgency of change. Before we go into the questions, we really want to connect here, because it fits very good, to a very interesting topic of point source capture. We already have the next speaker waiting in the line, Claude Letourneau. And Claude Letourneau is President and CEO from Svante, Canada. Can we get Claude in the line? Hey, Claude.
How are you?
Very good.
Greetings from beautiful Vancouver.
Yeah, thank you. Can you show outside the window a little bit?
Oh, I could, but it's a beautiful view. I guess I could do that, yes. If you see this. So this is my view.
Oh, that's it. Thank you, Claude. Just give a quick introduction on Svante. Svante offers companies in industries such as concrete and steel making so very CO2 intense industries, a commercial viable way to capture large-scale CO2 emissions from existing infrastructure. And
Yes,
you're doing this with point source capture. Claude, the stage is yours now.
Thank you very much.
Thank you.
First of all, I'd like to thank Christoph and Jan for inviting us to participate in this conference. We crossed paths about 15 months ago and created a partnership to see if we could help each other. And I think the conclusion of this came out last week with the DOE announcement of a demonstration project that we will do together next year in California, where our filter will be applied to the DAC system that Climeworks is developing, and hopefully will help them reduce the cost of their system as we scale up our technology. So quite pleased to be in there. So let me flip to the PowerPoint presentation that I have quickly. Can you see this one? Yes, I guess you can. Great, excellent. So, you know, what I'd like to do in this forum for the next few minutes is to share with you our thoughts of how to build a CO2 marketplace. It has to be economical at the end of the day if you want the market to deploy trillions of dollars to address climate change. So we're focusing on hard to abate emission coming from industrial sources, such as industrial boiler from flue gas, and we've using natural gas. And we have a demonstration project that we've built over the years, and it's in operation now today. You'll see a video in a few minutes. And that facility is using solid sorbent with our unique filter at a capacity of about 10,000 tons per year. It's in Saskatchewan, Canada. And we're very proud of the operating performance that we have so far at that scale. I think it's probably one of the few plant using solid sorbent at that scale that was ever built in the world for such CO2 separation. And then we have a roadmap toward focusing on cement as a market. And also DOE announced last week funding of a pre-feasibility study for a first commercial plant on a cement plant owned by Lafarge-Holcim in United States, in Colorado, for 2 million tons per year. And we will be leveraging the 45Q tax credit. So the economics of that project has to be done in such a way that we can basically capture and store the CO2 for $50 per ton. And the only way you can monetize this project is to use the 45Q tax credit. So we've put together a consortia of stakeholders from the emitter side, which is Lafarge-Holcim with their cement plant, the off-taker, which would be Oxy, using it for CO2 storage, and then us being a technology provider, we made a partnership with Kiewit to be an EPC partner with us to build that plant. And Total has been a project sponsor as well. And to feed this pre-feasibility study, we're currently in the process of commissioning a 1 ton per day plant using a brand new solid sorbent material based on a MOF material at Lafarge-Holcim here in Vancouver on a cement plant. And the data of that pilot plant operation will feed the pre-feasibility. Now, the third project that was approved by DOE last week, we were quite lucky to get 3 out of 3, is a second of a kind plant to about the same size as what you see at Husky that will be built at Chevron in California. And so we can demonstrate the applicability all the way from a 4% CO2 stream that would be coming from a natural gas power plant all the way up to a blue hydrogen plant using steam methane reformer all the way up to about 16%. So quite excited about all these 3 projects that we're looking at. So for us, the value chain is the source and the sink. So the source, we obviously are focusing our business entry in the marketplace on industrial emissions. Cement is the key focus. The blue hydrogen is the second one that we are targeting. So we can tag a carbon capture plant to a natural gas steam methane reformer to make blue hydrogen with a very low carbon footprint. And as a complement to Climeworks, we are trying to work with them in applying our filter for air capture as a supplier of filters to a solution that will be provided by Climeworks. So all of the CO2 that we would be capturing can end up into 3 places, as was probably mentioned earlier by others. But we see offshore and onshore storage worldwide to be deployed, potentially about a 4 to 5 gigaton potential. Here in North America, we're fortunate that we have a tax credit of 45Q at $50 to pay for this. And then we see the co-storage with EOR, probably a 1 to 2 gigaton potential, where there's a combination of a $20, $25 cost or price that the oil and gas are willing to pay for the CO2 to be stored in an EOR, and then the 45Q gives you an additional $35, so making it around $50, $55 revenue stream for these plants. We would like to work on utilization aspect. We have a couple of demonstrations we do at Lafarge on cement, but we see this market being more limited in a range of 20 to 50 million tons a year, and the price point there is a bit higher. So what you're going to see now is a short video of the facility at Husky. So you'll see the inside of that plant and the way the process works. And you also will be able to see the manufacturing plant we have in Vancouver, where we do the filter manufacturing. And it's all designed for mass production at the gigaton scale eventually. So let me just move to this video.
The Earth's vast forest.
Okay, I guess you're not seeing it. Hold on. Sorry. Nobody works and technology.
The Earth's vast forests and oceans are finely tuned and efficient natural systems for absorbing carbon dioxide, but they have reached their limits. Svante is committed to lending nature a hand by preventing CO2 generated by the world's key industries from entering the atmosphere. It's happening here in Saskatchewan at a pilot test plant with Husky Energy. For the first time at an industrial scale, Svante's technology is capturing 10,000 tons of carbon dioxide per year. Our approach is tailored specifically to the challenge of separating CO2 from nitrogen contained in the flue gas generated by industries such as cement, steel, and oil and gas. At this groundbreaking facility, gas that is normally vented through a smokestack is diverted to the Svante capture system. Dilute flue gas enters a continuously rotating platform where carbon dioxide is trapped by Svante's proprietary filters. These filters are made with engineered nanomaterials that create a powerful adsorbent with a high capacity for CO2 capture. A sugar cube-sized quantity has the surface area of a football field. As the platform rotates, the CO2 is safely released from the filters and exits the system purified and pipeline ready for storage, all in 60 seconds. With a capital cost at less than half of existing technologies, Svante makes industrial-scale carbon capture a reality. A single Svante plant can capture 1 million tons of carbon a year, equal to eliminating the annual emissions of more than 200,000 cars, or doing the work of 10 million trees. Svante offers companies in emissions-intensive industries a commercially viable way to capture large-scale CO2 from existing infrastructure. A powerful incentive for industry to join Mother Nature as an ally in the fight against climate change.
Thank you.
Claude, this was really a powerful video in the end, and I think you really have a powerful solution and technology with point source capture. We now go to the discussion with the audience. We want to say thank you to both of you. And first question goes to Keith. Keith, because below now you have a good overview on different climate solutions. What if you compare like natural negative emissions like afforestation with direct air capture?
Oh, well.
I think we need to talk about this subject today.
It's one of those, how long is a piece of string? So when it comes to the overall kind of like a mosaic of carbon dioxide removal technologies, we're very much at the start. So we have a relatively good idea of the capacity of forests to absorb carbon dioxide, but the conversation of how much land can be set aside, how much area can be reforested, and how that competes against other uses such as farming is still an open question. The same goes for soil carbon as well. So we have ideas that these things can work, but when it comes to quantifying at what scale and at what permanence the CO2 can be removed at, there's still a big question mark there. The same also goes for bioenergy and CCS, which is known as BECCS, and to a certain extent for DAC and CCS due to constraints on storage capacity. So when you add all these together, you end up with carbon dioxide removal being important, but definitely not being unlimited supply. It will be a limited amount of carbon dioxide removal to make up for the very, very hard to abate sectors and to rewind some of the damage we've done already to push us into net negative. But we definitely can't make up for all our emission sources with negative emissions technologies or with natural solutions.
Keith, you talked about land use. So if you compare afforestation to direct air capture, just to give the audience a picture, what is the amount of land use necessary?
So, well, it really depends. So I don't think it's useful comparing land use. So I should say that on my spare time, I do plant trees and forests because it's fun to do. I would say planting a forest, the least good reason for that is actually the carbon dioxide removal element of it. We talk about nature conservation, we talk about restoring biospheres. An issue that you actually have with DAC, which is the opposite, is that it doesn't really produce that many other benefits. Its only benefit is reducing and removing CO2 from the atmosphere. So if there is a competition between which route you would prefer to go, afforestation and nature-based solutions may offer more co-benefits, but as I said, they're very, very limited potentially on scale. So DAC has that advantage where it potentially can have a wider tail and be deployed on a larger scale, depending on how much CO2 transport and storage we develop.
Keith and Claude, we always have many questions from the audience, so I would give the microphone now to the audience, if this is okay for you. So are there any questions? Please here, first row. Yeah.
Yeah, this is Roland Dittmeier from KIT in Karlsruhe, Germany. The question goes to Claude. I would like to know the tolerance of your adsorbent against contaminants in these flue gases, because this is for point sources often really a problem.
This is a very good question. So when you address industrial emission, especially cement, and this is probably the most harsh environment you can think of, you have SOx and NOx and level of oxygen that would affect any amine type system. So what we've developed is a novel material called a metallic organic framework, MOF, that has a unique property of not having amines inside. So therefore we are not sensitive to SOx and NOx. And we have demonstrated that these MOF material can withstand the harsh environment of a cement plant. So we are now ready to scale up to the tonnage level with that material. We've been testing it for many years and produced a lot of kilograms of this material. And now we're moving into a larger scale demonstration. So the unit at Lafarge, the 1 ton, will be equipped with the sorbent material, and the one with Chevron next year at the 30 ton per day size, which requires in excess of 3 tons of material or so, will also be done with this MOF material. The other contaminant obviously is water, and then the issue that you have with many of the sorbent material is that they pick up a lot of water. The MOF also has this, but we were able with our rapid TSA to adapt the performance of our MOF to be able to withstand the moisture swing that is normally seen in a temperature swing system.
Thank you, Claude. More questions from the audience? No. All right. So that was a great session with you. Thank you both for joining us here at the Direct Air Capture Summit. Hopefully next year we can meet in person. But this year is a special year. So one more view out of your window, please.
Okay. Hold on.
Ah, beautiful. Okay. But Zurich is also beautiful. Okay. See you next time. Bye-bye, Keith. Thank you so much. Bye-bye, Claude.
Yeah.
We now switch to Norway. Have you heard about Northern Lights already? Yes, I think so. Huh? Kjetil Wilhelmsen, the new business development director for Northern Lights at Shell. Kjetil, you are with us. Welcome.
I am. Can you hear me?
Yeah, we can hear you very well. We can see you very well, and welcome to the Direct Air Capture Summit.
Thank you very much for inviting me.
Let me introduce the Northern Light carbon capture storage project as part of the Norwegian full-scale carbon capture project, capturing and liquefying CO2 from industrial sources in the Oslo Fjord region for transportation by ship to an onshore terminal in the Norwegian west coast. The use of ships to transport CO2 from industrial emitters is a unique solution and enables permanent storage of industrial CO2 volumes across Europe that would otherwise have been emitted. Kjetil.
That sounds like my presentation in a nutshell.
That was it, huh?
Yeah, that's it.
You would like to continue?
I can continue,
okay.
Sure. Thank you very much.
Thank you. Can you share your presentation if you have a presentation?
I can. I thought I was actually doing that.
Yeah, perfect.
New share, indeed. Can you see it now?
Yeah, now it's both perfect. Thank you.
Okay, and then let's have the... Okay, so look, thanks again for inviting me. Indeed, you summarized it quite well there. But maybe there's a bit more to say. You see three logos at the top right-hand side corner there. Total, Shell, and Equinor. As you said, Shell is my mother company. We are an unincorporated joint venture today, but we are going to incorporate ourselves. And each of these three companies have a third equity in that company. And we are working together in the project team seamlessly, seconded in from all three companies. So I think that has proved to be quite powerful. We are able to tap into a lot of knowledge and resources in our three companies. Now, let's see. There we go. So we had a major milestone, and this might be, so some of you have heard about us and seen some of these slides before, but this is relatively new. This is from May, and we took our investment decision in Northern Lights. That means that on the Equinor, Shell, and Total side, we decided that this project is worth going for from a techno-commercial point of view. And you see here a snapshot of the website of the Norwegian Ministry of Petroleum and Energy, where they are basically saying this is an important milestone for the project. Meanwhile, the two other capture plants that are also part of the overall project have also taken their respective FIDs. And we are now currently waiting for Norwegian authorities to go ahead and say yes. What that means is that the government had their budget conference last week, and they are presenting their proposal to the state budget for 2021 to Parliament in October. And then hopefully, formally, there will be a decision in December, before Christmas this year, that we are going ahead with Northern Lights in Norway. Now, where are we coming from? Well, it's the energy transition, of course, and we are trying to figure out the role of CCS in that. At an aggregate level, I think a key question would be, how do we decarbonize the economy while at the same time maintaining industrial activities, value creation, and jobs? I think this is a question that we're all asking, both in the companies that I am representing here, and also, of course, policy and decision makers in the public sector. At the company level, we are also asking, what is our role in this? What will our shareholders want us to do? What can we afford? And these are questions that we are trying to answer on a daily basis, if you like. You see the ETS price there on the left-hand side illustration. I'm not saying that this arrow is an economic, is sort of a very correct line, but there's certainly no doubt that the ETS price has gone up over the last couple of years. That is very, very important. It is driving a lot of the interest we're seeing from potential third parties, so large industrial CO2 emitters across Europe. And I'm coming back to that. But let's go back to what the Norwegian full-scale demonstration project is all about. On the right-hand side here, you see the southern tip of Scandinavian Peninsula, Sweden and Norway. Like you said in the introduction, in the Oslo Fjord region, in Oslo, there's a waste-to-energy plant, recycling plant, and a couple of hours drive south, there is a cement plant. So this goes right back into Bellona's example, of course, also previously. We're then going to take the CO2 in liquid form on a ship and transport it to an onshore facilities on the west coast of Norway, just northwest of Bergen, the second city of the country. And you see on the west, on the left-hand side of this slide, you see then the ship, you see the onshore facilities, you see a pipeline going offshore, you see a subsea facility, and you see a well, and you see a subsurface storage complex in the geology. So our scope for Equinor, Shell, and Total is to the right of that red line there. Of course, we have a very, very important interface with, in the Norwegian demonstration project point of view, the two plants you see in the Oslo Fjord region. But this can, of course, be expanded, and you see that on the right-hand side again, third parties on a dotted line coming in from continental Europe. Which is very, very important, because there is really no point in doing this if this was only for the purposes of Norwegian CO2 emissions. As you might know, we have hydropower for electricity generation, and it's a small country, 5.5 million people, so it doesn't really make any sense. This has to be a European dimension to this project. A little bit more maybe on the concept overview of what we're trying to do here. I'm not going to go into all the details here, but you see this is the same image as we saw on the previous slide with a bit more detail. At the bottom here, though, you see some of the scales that we're talking about. So on the y-axis, 1.5 and 5, that means capacity that we are going to invest in. And when I said that we took our FID in May, that was for the 1.5 million tons a year, so the first number on that y-axis. As you see, as you go right on that part of the slide here, you see the pipeline goes up to 5 million tons. It's just much less inefficient or more efficient to put in place a larger pipeline than two smaller pipelines next to each other. So we're building for success, and we have decided to go for a pipeline that can take 5 million tons a year. So incremental 3.5 up from 1.5 million tons. So those would be our phases 1 and phases 2. You can see that it is modular in the sense that we can add new capture sites, and you have that here. The two represented on this slide would be the cement factory and the waste-to-energy plant in Norway, and then we can add modularly also ships as we need that. The onshore facilities are designed for 1.5 million tons. The pipeline, like I said, 5 million tons, and then there's always going to be a question around the capacity of a well, an injection well. But we think that we have fairly good control, and that one well will be able to take 1.5 million tons a year. The two plants that we have in the Oslo Fjord region each have approximately 400,000 tons a year of CO2. Adding up to 800,000 tons, that means that I have 700,000 tons a year to sell to third-party volume providers, CO2 emitters, across Europe. If we have commercial success, we are then going to take an FID on this phase 2, giving me an incremental 3.5 million tons of CO2 capacity. Now, is there a business opportunity? We think there is, no doubt. On this image here, you see a lot of dots, and each of these dots represents at least 100,000 tons, most of them quite a lot more. And you see on the right-hand side here, the sectors that we believe have the largest potential. Waste to energy, cement, biomass and biofuel, refineries, steel, natural gas monetization like hydrogen production and electricity production, fertilizers, data centers for Silicon Valley kind of companies, and obviously direct air capture. And you will notice that a lot of these sectors that I'm talking about here have nothing to do with the traditional oil and gas upstream business. So even if you can say that refineries and natural gas monetization would be good fits with what Equinor, Shell and Total typically are doing, you can also see that we are hoping to provide a long-term solution to European and global CO2 emissions, even after the energy transition has taken completely place. So, in other words, when Europe is full of solar panels and windmills and batteries and smart solutions, smart grids and so on, there will still probably be waste production and there will be cement production and so on. We will then be there and we will provide a solution. So that's important to us. So just very quickly, the numbers that you saw on the previous slide, you see the grand total in Europe, well, 1.5 billion tons a year. So that is a bit more than my 1.5 million tons a year of phase one and 5 million tons for phase two. And when I look at the map a little bit closer to home, closer to Norway, i.e. Northwest Europe from, I don't know, from Normandy in France up to Finland, I get, and close to shore, I get 580, 600 million tons a year. So again, very, very large scope. So what have we done commercially? Well, we've signed 8 MOUs, and we're close to signing a 9th one later this month. You see them here on the left-hand side. What we like about this list is that it is a list representing a wide variety of different industries and a wide variety of different European countries. And I'm happy to say that we have one now with ETH Zurich. That was the last one we signed, and that is providing for very stimulating conversations with the team at the university. You see the typical content there also. Logistics studies, very, very important. Logistics is a key item to get right. CO2 specification, what kind of CO2 spec do we need in order to accommodate, to take delivery of CO2? Very important. The third one there, roadmap towards potential startup, that is code for how do we get commercial agreements in place. Then joint advocacy is still needed, both in Brussels, but also in national capitals and other places. And then there is a need for bilateral arrangements between Finland and Norway, Ireland and Norway, Switzerland and Norway, and so on. And we need to facilitate that also. If I look at the MOU partners, but also a lot of other companies I'm talking to across Northwest Europe, you see that it's a little bit hard to see here. That's why I put approximately 75 million tons a year on the right y-axis there. So if I add up companies that we have a sort of a positive dialogue with, I'd say that by 2050, or actually by 2040, that would give me a plateau of 75 million tons a year. So that makes a difference. Now, having said that, no one believes in their right mind that this is going to be realized, all these volumes, but it does give a very, very interesting image of the scope and of the interest, the commercial interest that we're seeing from European emitters today. And I suspect that as the ETS price continues upwards, well, that's a guess, of course, that it will continue upwards, but I think the signals we're seeing coming out of Brussels point in that direction. This picture is going to be even bigger in next year's conference. So I think the last slide then to round it all off is also very important, and that comes into that surely. We are in effect trying to create a European CCS ecosystem, and the virtuous circle. So we are constantly being contacted by a number of companies across the value chain. So capture companies want to talk to us, of course. Transportation companies want to talk to us. That would be road, rail, different kinds of sea-going vessels. People doing storage, industrial storage or liquids in my major ports around the world want to talk to us. Even non-technical disciplines like law firms and other companies want to talk to us to see, is there a role for us to play in the CCS value chain that you're establishing? And we accommodate those conversations with great pleasure, because we really believe that this will stimulate to innovation, cost reductions, and then jobs creations also. And you see on the right-hand side here, sort of an illustration of what this can look like. And you see also a number of companies here that we are public with, if you like, because these are companies that we have a project of common interest status with. So PCI status in Brussels. Companies like, representing Ireland, the UK, France, Belgium, the Netherlands, Germany, and Sweden primarily. I think in the next round, you'll also see Danish, maybe also Baltic and Finnish companies adding to that list. So I think that's those were the slides I was thinking about that I wanted to share this afternoon.
Kjetil, I believe we have many fans of Northern Lights here in the room.
Great.
And now we have some more after your talk.
Okay.
What would you say, could the Northern Light approach be replicated to other parts of the world?
I am sure. And we are, we're also being contacted by people in other parts of the world, in particular Southeast Asia. So say you're in Singapore, you know that you have a lot of CO2 emissions. You don't have geology to store CO2, but you have geology in Malaysia or Indonesia.
Yeah.
So they are interested in understanding, how are we thinking around the shipping solution, for example? There are other parts of the world also where you can see sort of this branching out. And also, of course, other parts of Europe. I mean, Eastern Meds, Southern Europe, there is a lot of geology in North Africa or in Italy where you can store CO2. For the time being, though, our focus is, like I said, sort of from Dunkirk, approximately Ireland, and then up to the Baltics in Finland. That is sort of our first geographical area. But yeah, I mean, we are talking, with our friends in ETH Zurich, and you wouldn't typically think about Switzerland as a northern European coastal nation, but there's clearly interest from Switzerland, from inland German emitters. So this is just coming to continue rolling. I hope.
Thank you. Let's give the microphone to the audience. Here's the first question.
Actually, two questions. First is, maybe I missed it, average cost over the next 10 years for transport and storage. And the second is safety of storage, considering, for example, tectonic movements or migration of CO2 where others might drill into, or pressure increase in large scale. So do you have a clear positive message on that?
I think I do. So let's take the last one first. Safety is of paramount importance to us. I mean, it's, not being able to say that we are storing the CO2 safely and permanently would completely undermine our business case. So it's something that we put a lot of effort into. And of course, you can say that this is one of the reasons why you need large international oil companies like Equinor, Shell, and Total to do this, because what we have been doing for 100 years in the upstream business is to understand the geology and to find oil and gas that has been trapped by geology. So in a way, we're doing exactly the opposite now. And of course, in Norway, we have all three companies heritage. We understand the geology, we feel very well. And so we have put a lot of effort into the exact storage location that we have been awarded by Norwegian authorities for this exact purpose, to make sure that we have the right kinds of sealings, the geological sealings in the geology above the exact horizon where we're injecting the CO2. I should have said maybe that we have already drilled the well that we're going to use to inject CO2. And one of the advantages of drilling the well early was to make sure that the geology is indeed as we thought it would be. So that means that we drilled through these ceilings that we will then rely on so that the CO2 will not make it out. On top of that, of course, we're putting into place monitoring programs, and that is part of the deal we have with the authorities. We will have to monitor the CO2 and the movement of the plume, the injected CO2, for decades, of course, before we can relinquish the acreage back to the authorities. So that's on safety. I should maybe also say that Equinor in Norway are operating 2 CCS projects, one Sleipner, which is an offshore oil production in the North Sea, and Snøhvit, which is an LNG facility in the Barents Sea in the very far north. And so they, of course, have a lot of experience with monitoring CO2, injected CO2 in Norway. In Shell, we have projects in Canada, in Australia. Total have their projects. So, you know, adding all those resources and that experience together, we like to think that this is safe. But again, we're going to monitor this for decades to come once we start injecting. When it comes to costs, we have not gone out and said anything about the costs of the capex for this project, but it is expensive. What we have said publicly is more related to the tariff that we are going to need from potential third parties across Europe. And what we have said there is between, I don't know, 40 to 60 euros per ton. We take delivery with our ships in Northwest Europe, in a major harbor, say in Dunkirk, in Antwerp, in Ghent, in Rotterdam, in Amsterdam, in Hamburg, these kinds of places, Stockholm, maybe. Stockholm is further away though, so that makes it a little bit more expensive. So that will be kind of the range that we are aiming for in 10 years from now. So we're not there today, but we believe that there will be a lot of cost reductions throughout the whole value chain. And we will then be able to make it to that kind of tariff range in order to make it interesting for us as an investment opportunity. And then with the ETS price going up to those kinds of levels and beyond, come 2030, this should hopefully be a business opportunity that makes sense even without massive investments from states, entities, or the EU in the form of subsidies.
Last question from the audience. Kjetil, this was a wonderful session. Thank you for the introduction of Northern Lights. Thank you for joining us in the remote stream here. We hope very much that we meet you next year live in Zurich at the Direct Air Capture Summit 2021.
I'm looking forward to joining you physically next year.
Yes. So greetings, have a great day, and thank you for your wonderful presentation. Thank you.
Thank you too.
Now it's my very special pleasure to introduce the first lady speaking here today. I don't know what's up with tech and ladies in the tech industry. How is it at Climeworks? 20%? 30%. Okay, good. That's okay. Getting better. Edda. The name is quite complicated. We have Dr. Edda Sif Aradóttir. Is it right? How do we spell your name?
Edda Aradóttir. It was almost right.
Okay, thank you. Nice to have you here. You're live from Reykjavik now.
Yes, that's correct.
We think you run a really interesting program there. So thank you very much for joining the Direct Air Capture Summit.
Thank you for inviting me.
Edda is CEO at Carbfix. And Carbfix is an Icelandic company which captures CO2 from emissions and turned it into stone underground. How long are you doing? How long are you doing this now, Edda? Is it quite new, huh?
No. Study operations since 2014.
14, okay. Mm-hmm.
Yeah.
Prior to Carbfix, you were acting manager and Department of R&D and Innovation, head of innovation and strategic planning at Reykjavik Energy.
Correct.
And you have a PhD in engineering from the University of Iceland. Edda, we are very much looking forward to listening to your talk. If you have any slides, you can share them here. We already see small slides. That's super. All right, stage is yours, Edda.
Thank you. Thank you for the introduction. I would have very much liked to participate in the summit in person, as I planned on doing, but due to COVID, I was not able to travel to Zurich this week. I do, however, hope that this type of a hybrid event, as we are experiencing now, will become the new norm, because it would significantly benefit our climate and also relieve the air travel conscience for those of us that typically have to travel with planes to attend events such as this one. But anyway, enough about that. I'm here to tell you about Carbfix and the technology that the Carbfix team has developed to fight climate change. Carbfix turns CO2 into stone underground in less than 2 years through proprietary technology that imitates and accelerates natural processes. And the piece of rock sample shown on the slide is basalt, one of the most common rock types on Earth. And embedded in the pores and fractures of the gray basalt, you see white crystals. And these are carbonate minerals that contain solidified CO2. The Carbfix technology is applicable to both avoiding carbon emissions as well as removing CO2 already emitted to the atmosphere, and both of which are vital if we are to achieve our climate goals. Carbfix is a subsidiary of Reykjavik Energy, the largest geothermal energy and utility company in Iceland. And the Carbfix flagship project is located at the Hellisheiði geothermal power plant, which is operated by our sister company, On Power. There, we annually capture and inject some 18,000 tons of CO2 and actually some H2S with it as well from the power plant and have been doing so steadily since 2014. And since 2017, we've also injected CO2 captured from ambient air by Climeworks at the same site through an EU-funded project. Now, Carbfix started out as a collaborative research project between industry and academia in Iceland, Europe, and the US in 2007. And since then, we've scaled up and optimized, in just 7 years, an outstanding team of scientists, engineers, and craftsmen turned what was just an idea on paper in 2007 to a proven industrial process. And this happened in just 7 years. But since 2014, we've scaled up and optimized capture and injection operations, increased our understanding of subsurface processes, and continued further developing the method to maximize its potential impact on climate. This schematic explains briefly what's going on at our site at Hellisheiði. So as I said, we've now reached the status of being a proven industrial scale methods for conditions that are similar to those that are found at our power plant site, which is where we have relatively fresh basalts and access to a source of fresh water. The Carbfix CCS process operated at the power plant, shown on this schematic, involves capturing otherwise emitted CO2 by simply dissolving it in water. And the resulting water phase, which is essentially just soda water, is then injected into nearby basaltic formations, where natural reactions take over, rapidly transforming the captured CO2 into stone. And since 2017, Climeworks has used part of the renewable heat and power generated at the power plant to power its direct air capture module. And we have taken the stream of air-removed CO2 and co-injected with the downgoing stream from the power plant. And here we have the chemical equation explaining what happens underground after we inject the CO2. Basically, the transition of transforming CO2 into stone happens in two steps. Firstly, we actually partially dissolve the basaltic host rock that we inject the CO2 into. And this happens when the acidic fluid that contains the dissolved CO2 comes in contact with the basalt. Thereby, we release divalent cations, calcium, magnesium, and iron, into the water phase. And these can then meet up with the dissolved CO2 to form carbonate minerals. And this is, in fact, nothing but an imitation and acceleration of a process that nature has used over millions of years to regulate the long-term CO2 concentration in the atmosphere. And in fact, rocks are the largest carbon reservoir on Earth. All the carbon that exists on Earth, be it in the atmosphere, in living creatures, or dissolved in the oceans, is derived from rocks and will eventually end up in rocks again through the carbon cycle. So what we do is speed up nature's way of permanently storing carbon using science and innovation. Now, the cost of industrial scale CO2 emission avoidance at Hellisheiði by using the CarbFix technology is lower than $25 per ton. And included in this overall cost is the capture, transport, injection, and monitoring. This is significantly cheaper than most cost figures reported for conventional carbon capture and storage. For example, in relation to coal-fired power plants, enhanced oil recovery, etc. And furthermore, this cost is comparable to the current price of carbon quota in the ETS market. Now, these are on-site costs for this particular site. Costs of installing a similar CCS chain at other locations will somewhat vary, as they are dependent on different parameters, such as scale of operations, concentration of CO2 in emission streams, depth and number of wells to be used, distance to injection site, etc. But we can say that CarbFix is undoubtedly a very economic way of avoiding emissions, provided that favorable storage formations are located in vicinity of emission sources. Now, with respect to carbon removal, it is also difficult to say exactly what the cost of permanent storage with the CarbFix technology would be, because again, the exact cost will depend on several project-dependent parameters. For example, the amount of CO2 to be injected, project lifetime, number of wells and depth of them, etc. But generally, we would be looking at costs of the same order as shown on the previous slide. And in any case, cost of CO2 mineral storage in relation to direct air capture would be a small part of the total cost, as the capturing part, the direct air capture part, would dominate the overall cost. Now, if we look at the broad perspective to climate action and limiting temperature increase on our planet to well below 2 degrees, we are all aware that we have a huge task in front of us. We need to avoid over 1,000 gigatons of emissions in the next 40 years, and thereof, CCS has to provide 190 gigatons. And basically what this means is that we need to increase our storage capacity on the global scale by 25% every year for the next 40 years. And as we are increasing our capacity for CO2 storage, we will be scaling up carbon removal as well, for example, through DAC technology, which will have to play an increasingly significant role in climate action in the coming years and decades. And coupling direct air capture and mineral storage of CO2 allows for permanent removal of previously emitted CO2. By combining further development and upscaling of DAC and CO2 storage technologies, we can achieve synergy, increase efficiency, and get the most out of climate investments. But what role can carbon mineral storage play in our climate action? Well, basically, it can play as big a role as we want it to play. If we look at the most favorable storage formations throughout the globe, shown on this global map here, over 5% of the continents and the majority of the ocean floor are made up of basaltic rocks, which are ideal for turning CO2 into stone in. And altogether, the storage capacity in basalts has been estimated to exceed 100,000 gigatons, which is orders of magnitude larger than emissions from burning all fossil fuel available on Earth. And I would also like to point out that basalts and other geological formations favorable for CO2 mineral storage are typically located in other locations than the formations used for classical storage of supercritical CO2, as was explained in the previous talk. The carbon mineral storage in basalts therefore opens up large regions that have previously not been considered as candidates for CCS. And the two different CCS methods explained in this talk and the previous talk, therefore very well complement one another, making CCS a possibility in more varied locations throughout the world, both onshore and offshore. Basalts and other reactive rock formations were for a long time largely overlooked for CCS implementation, but this has been changing in the recent years. And on the figure shown here is a map of onshore and offshore geologic formations within Europe that are favorable to CO2 mineral storage. And altogether, these formations could store between 6,000 to 15,000 gigatons of CO2. And a similar map for the US would show us that similar formations on US ground could store between 8,000 and 20,000 gigatons of CO2. And of course, some of these rocks can be used for not just avoiding CO2 emissions and turning captured CO2 from emission sources into stone, but also for mineralizing CO2 removed from the atmosphere. And as already explained, this we have been doing at the Edda Sif site in collaboration with Climeworks since 2017. We all share the same atmosphere, and a CO2 molecule emitted in New York will have reached our site in Iceland in just 4 days. And through joint application of DAC and Carbfix technologies, we can recapture this molecule and turn it permanently into stone underground. Over the past 3 years, we've learned and demonstrated the synergistic effects of operating direct air capture and mineral storage of CO2 in vicinity of energy and industrial production that allow for access to renewable heat and power. And recently, we announced plans for upscaled operations, which has already been discussed here today. And we are very much looking forward to seeing additional DAC modules being installed at Edda Sif, as well as commissioning new injection wells. Our mission at Carbfix is to be a key instrument to tackle climate change and turn as many tons of CO2 into stone underground as possible. And our goal is to reach the gigaton scale by 2030. Our scale-up concept consists of on-site carbon capture and mineral storage, where possible, as well as capture and transport to mineralization hubs where geology is not favorable in vicinity of emission sources. And in all cases, implementing direct air capture at injection sites could further add to the source of CO2 for mineral storage and increase investment efficiency. But if we are to meet these ambitious goals and make our vision come true, we have to continue research and innovation in the field of direct air capture and CO2 mineral storage. For example, we have to continue optimizing efficiency and resource requirements. We want to further develop our injection technology so that we're able to use seawater and the ocean floor for mineralizing CO2 in. And we have to develop and scale up transport networks, as well as flexible and scalable CO2 mineral storage hubs. Now, I've reached my final slide, and I'm sure most of you, if not all, have seen this figure from the Economist article that was released in July, referring to carbon removal as the next big oil. I did not particularly favor the analogy with the oil industry, but of course the aim of this analogy was to give the reader an impression of the scale that we must bring climate solutions to. And it is the responsibility of all of us participating in this summit today, as well as all of our colleagues, to create a new climate-friendly industry that involves avoiding CO2 emissions, as well as removing CO2 that has been emitted to the atmosphere. And if we succeed, we will not only do our part in ensuring that we reach our climate goals, but also create a positive impact on society, as this new industry will create hundreds of thousands of high-tech jobs in the coming years, which the global economy is in desperate need of. So with that, I would like to thank you for your attention.
Edda, it seems like Iceland is the perfect place for carbon capture storage and carbon dioxide removal due to your green energy and your wonderful stone underground. Could you imagine to expand somewhere else in the next step?
Oh yes, absolutely. We are actually already taking the first steps in doing so. And next year we will be starting pilot injections in Germany and Turkey. And there are several other projects sort of being scoped, and hopefully we will be able to test out our injection in even more locations as well. Because as shown on the map in my presentation, we have favorable sites throughout the world.
Yes, seen. And I believe there are additional questions from the audience, so I would give the microphone to the audience. In the last row. Sorry, you have to run. Please.
Hi. My question is, how much water do you need to store 1 ton of CO2?
This somewhat depends on the pressure that's used for the injection, and this can vary from site to site. The way we did it originally was that we needed 25 tons of water per ton of CO2. But I would like to emphasize that this water is actually coming from the reservoir that we inject the CO2 into. And after the CO2 has been mineralized, we can recirculate the water. And this is what we've been doing for the past few years. In our upcoming project, we will be bringing down the amount of water needed, but in all cases, we will need significant amounts of water to dissolve the CO2 in, because this facilitates the speed of reactions. So as I say, we will need the water, but we can recirculate it after the mineralization has taken place.
Any more questions to Edda?
do you consider yourself cost competitive to standard storage in Europe over the next, say, 20 years?
Oh yes, absolutely, definitely. For sure, yeah. As I was trying to show with the cost figures on the slide, of course, in all cases, the costs for each project is, of course, dependent on some of the parameters that I was describing. But our technology allows us to make considerable cost savings when it comes to the injection method per se.
Take for CO2 to be mineralized?
I'm sorry, could you repeat?
Can you
I didn't
repeat?
catch the question.
So how long does it take for the CO2 to be mineralized?
Here at our site in Iceland, it takes less than 2 years. This will be somewhat dependent on the geology at each site, the age of the rock that we inject into, etc. But this is our long-term experience here in Iceland, that the reactions are turning the CO2 into stone in less than 2 years.
All right, that's it. One more. Edda, one more.
One more. My name is Roland Dittmeier from KIT in Karlsruhe. I understood that the carb fix basically works with CO2 dissolved in water. Now, if you combine direct air capture with this technology, isn't it that you first purify the CO2 and then you dilute it again by admixing it to water? Doesn't that have some thermodynamic energy disadvantage? Wouldn't it be better to do the capture step then also with the liquid absorbent?
Yes, I mean, this is one of the points that I was referring to, that we can further improve the joint application of these technologies. Of course, the Climeworks technology was developed independent of the CarbFix technology, but of course, whatever we can do to sort of maximize the overall efficiency of these two separate technologies for the scale up that we are aiming for, that would of course be very beneficial. So this is something that we would very much like to work on in the coming years.
So that's it. Edda, greetings to Reykjavik. Thank you for the amazing insights. It was really, really beneficial. And I hope to see you next year here in Zurich.
Absolutely.
Thank you. Bye-bye.
Thank you. Bye.
So, ladies and gentlemen, now it's time to sum up the conference and the summit together with you to get the most interesting insights. And I want to get the founders and initiators of this event, Jan and Christoph, with me on stage and sum up with you together your top insights of today. Jan and Christoph, before we start, I know you are in this direct, come please on stage, this direct air capture industry now so long, and maybe sometimes you lose the external view, but for me it's really like the emergence of a new industry. It's the emergence of something really big new thing. In Trent we say the next big thing, and I think this is also what the economy said. And this is a new kind of business which is not only profit-oriented and not only people and consumer-oriented, because if you compare to other business, they all want to make profit and want to make customers happy. But for you, it's maybe more to make the planet happy. So maybe the planet is the main stakeholder on the business, and so it's about planet and purpose. Do you still feel this? Is this what you also feel in your daily work? Or are you more from the engineering side and want to improve and make it better and better? What is your perspective on the business you are doing?
Well, from Niels, you asked about internally, the purpose we're having. Maybe the Climeworkers in the room should answer the question. We are very, very proud and focused on our purpose. Like we talk and celebrate it very regularly. And clearly, Jan and I have been in direct air capture for the last 13 years, and we still go full steam ahead. And we can only do so because we are very motivated and by this purpose. This really is this intrinsic motivation to solve this
Can I ask, what is the purpose of Climeworks?
purpose is let's reverse climate change.
Yeah. Okay, so this is really a planetary
a
focus.
huge topic, yeah. But referring to your comment regarding, is it actually a business?
Yeah.
Yes, indeed, because it needs to be a business in order to become big, right?
Yeah.
Like we always say, or we are often asked, why did you start Climeworks as a limited, as a for-profit organization, and not as a non-for-profit organization? And the answer is, we want to have impact. We want to achieve those gigatons which were mentioned. And like if we take that, or like being an engineer, or the New York Times once wrote very nicely that we look at the climate challenge in mathematical terms or in number terms.
Yes.
If we look at the challenge ahead of us, say 10 gigatons multiplied by $100 or $200, it's 2 trillion. The accumulated sales of the largest industries in place, on Earth, oil and gas, are the same order of magnitude, and they are also for-profit. You have to become for-profit in order to achieve that scale, in order to unlock substantial investments.
So maybe this is a nice summary. So the direct air capture industry is about having a purpose. It's about putting the planet there. It's about making people's life better, and of course to make profit. So it's all 4P. It's like a systemic thing. Yeah? And what were your main insights from the summit today? Do you have the feeling that you pushed the direct air capture industry a little bit in the right direction with today's summit?
Well, I can start on this. I think in terms of, I was thinking before, what did I learn from today? And if I look back to the last 10 years, even 13 years when we started, I would say the last decade was about innovation, about development, about showing that that can work. So in 2017, we showed, hey, there is a plant and it actually does work. We have a commercial case. We might not be making profit with it, but it's like operating, it's going. And today, for me, it feels like looking forward to the next decade. That could be the decade of implementation. Yeah. So what we saw today, 3 direct air capture companies, very much advanced compared to where we were years ago, with very concrete projects in the pipeline that are set up, a roadmap. On the one hand, we were seeing, we couldn't imagine this 5-6 years ago when we were a tiny startup company. We were today inviting big industrial companies. So there were companies like Equinor, Shell, Total, big oil companies who are now thinking about how could we put CO2 underground. So thinking in global scales, in gigaton scales, there are players putting these pieces together. Mm-hmm. And there were states, there was a very clear and transparent roadmap from the state of California, showing us how could they become carbon neutral, what piece of technology do they need for that, with a clear timeline and with a clear scale and with clear numbers in it. So this is, if we transfer that to the next decade, this can be turned into something that really makes an impact.
Yeah. Good times for the direct air capture industry. You want to sum up any questions or insights from your perspective? Everybody's ready for the apéro.
Well, before we go to the apéro, with a little present for all of our speakers. Most of them are online. Thank you again for taking the detour, making yourself available today. Every one of you will get a 1-year Climeworks subscription to turn CO2 into stone. We hope in the meantime that all people here and all online participants have signed up for a subscription. And we hope you appreciate and enjoy the service of carbon removal. It is, well, a tiny company, tiny quantity when we compare that to the figures we talked before. But as we say, or we like to say, the power of small steps, and clearly those steps are, we hope, and that maybe as a message, we hope that today we gave you an impression that with, although being tiny steps, with the next steps we can unlock a very substantial industry in the next years.
I must say it was such a wonderful day with you, with the audience, with these amazing speakers. It was so much content, so much we could learn today. And thank you for organizing it. And thank you all for joining us and staying here until the end. It was a wonderful day together with you. And I wish you all the best for the direct air capture industry for the next years. And I hope you will do the summit again and again, because I think it's great for the industry to meet once a year together and to become a bigger industry. Thank you.
Thank you, Niels, and thanks for guiding us through this day.
Thank you.